That's also a thing which, like, this is only for one charger. Okay, so only one charger. This is one charger in one vehicle, like not sorry. This is across one charger only, but many number of vehicles are coming and charging there. So in that case, you can see that around 5 or 6 times this value has gone above the rated value. So the values, like different harmonics, higher values of harmonics can also be seen, which is above 1%. This is only, as I said, only for one particular charger the reading is taken. And just imagine when multiple, many such chargers are there and might be in a weaker grid, then there are possibilities of higher values of harmonics. And similarly, I was also telling the load also, if it is a truck or a bus, again, the magnitude of current will increase that is drawn from the grid. So in that case also, higher values of harmonics can be predicted. Okay, this is just a single value, like a small model, real-time model is shown here. And now, if you see, the harmonic emissions are within the limits because we have the IEEE 519 standard. I yesterday showed you, even for these automobiles, ASAE, they have given that they also follow this IEEE 519 standard only. So for that, if you see the emissions, they are within the limits. Okay. And harmonic order, if you see 5, 7, 11, 13, 17, 19, and 23 and 25 are higher, but within limits, but they are little higher. And higher harmonic values are possible when large charging stations are connected to transformers with many customers. So, like when more number of customers are there, electric vehicles are there, and fast charging, and they are connected to the same transformer, there are possibilities of aggregation and resonance and all these things. And another thing is the harmonic resonance in low voltage network with EV-PV combinations. So I was also telling you about the Homans from Netherlands, the EV-PV combination of resonances of harmonics we were looking yesterday. So those are also the possibilities when EV and PV come together and when PV is generating the maximum. Then high values of even harmonics, that is a fourth harmonic, may be due to frequency aggregation or direct current. So in this case, if you see, even the fourth harmonic value, usually the fourth harmonic value should not be present. This is this is the even harmonics, but even that around 1 amps, you can see here, high value is seen. Okay, so that might be due to some frequency aggregations, like low frequency components getting aggregated, or because of the direct current, like DC component in that. So these components may also affect the grid. Might be this may cause a saturation of the transformer, or but we did that measurement with this 1 amps. We simply tried with a transformer value of the inductors, and we tried whether it will saturate, but not much. But if this value goes little more higher, there is a possibility of saturation. So like such researches are also done, like we can see these components. So when more number of vehicle come, maybe this component goes high. If such a condition occurs, is there possibility that the transformers connected nearby in the distribution side, whether it can get saturated, or like even other studies are there when these lower order harmonics or the direct current component present here may saturate the RCD in the neighbor's house, or like in your house itself, the RCD is connected, because those RCDs also have the inductor component in that, whether it will saturate that. So it may occur, failure may occur. So such things can also be seen here. So these are very important things which we have to take into account when we are doing such studies. Another thing is the interharmonics. So I was telling you, interharmonics are the harmonics which are not the integer multiple, the non-integer multiple like 2.5 or 3.6. So such components are said to be the interharmonic component. So here the interharmonic component, I think zero point 0.5, then 3.5 and 11.5. So such components were measured, and those components are shown here. So you can see that this is the charging cycle, two charging cycles of two vehicles here. Okay, yesterday I had shown that. For those, you can see here, when there was a high kilowatt charger, you can see high values of these interharmonics, that too mainly during transients, when starting and stopping of those chargers, when the chargers started charging and stopped charging. Similarly, lower and this, you can see some values. Whenever these values are there, you can see the interharmonic component there. Okay, so this is a like a EV with small like not fast charging, because it has taken only a less, maybe less than 50 amps, and it is charging. So it takes 1.5 hours. For our case, if you see, when we are going for 5 hours or 8 hours, this is a fast charger only. But actually, the this charger is a fast charger. Within 10 or 15 minutes, you can charge it. So in that case, if you see, this is a little slow charger only, EV charger. For that case also, you can see interharmonics present in that you can see here interharmonic component, but the magnitude is less compared to the other one. And this is the other component, 3.5 component, that is also available. And even the lower 11.5, the magnitude is less, but you can see those, like when due to the switching, also switching inside the like whenever the switching of the converter occurs, during that time also large interharmonics can be seen. Okay. And what are the problems these interharmonics cause? So, or the superharmonics cause? That was one of the questions yesterday. Here also you can see from the grouping of interharmonics 0.5, 3.5, 11.5, which is was shown in the previous figure. It is inferred that the interharmonic component is higher during the transients at start and end of the fast charging. So that we saw that. An aggregation of interharmonic emission due to multiple EV charging at the same time can result in worst case instability issues of the control system. Okay, so like when more number of these EVs are charging, there may be aggregation. So such a study also we had done, and that paper we have just submitted it. And another thing is the impacts which are caused by these interharmonics. So many papers you can see in all these individual topics which I have mentioned here on these interharmonics. So if somebody is interested, you can take up. And this studies is little interesting and not very tough also. You take data, you analyze it, and you can come bring out some solutions. So you have power transformer saturation, then the interference with data acquisition systems, because these are high frequency component and they are also power power carrier communications and all, or if you see high frequency data which is being transferred, so it may interfere with them. Then unwanted tripping of relays or protection circuits, that is also a thing. So you can take so small relays and you can just inject these components and see whether it is like at a particular, say 2 amps, it has to trip. And with these supraharmonic component, if it is not tripping at that particular time, then these are all the problems which it can cause. So what magnitude of these supraharmonic, because somebody yesterday were asking what will be the magnitude of this. These are very feeble small magnitudes, only in few milliamps or very small value. But at what even that small milliamps, what all problems it can create. So for that, what we have to do is we have to create those small milliamp component of those frequencies, and we have to try injecting that in some protective device, a protection device or relays or like such things, and then we have to infer that what problems like how it is reacting to it. Okay, so instability in phase lock loop based converter control scheme, even with very low amplitude. Okay, so it may affect the phase lock loop. So switching of the converters may be affected. High flickering and monitoring on image fluctuations. So monitors image fluctuations or high light flickering, all these things can occur. Aging of thermal effect, urging and thermal effect. So it increases the aging, like heating and other effect can be brought. Subsynchronous oscillation of the system, so that's also possible. Then ability to excite dominant resonances, the interference with harmonic components and harmonic filtering mechanism. It interferes with such systems, and errors firing of thyristors. So, like by mistake, the thyristor may get fired because of these components. Okay, so these components may, like say, because those are control signals. So when these component comes and interfere with that, the magnitude may slightly increase than the existing. So the thyristor may get fired. So such studies can also be done by injecting these components, and we can study like because of this component, is there any tripping occurring or anything. And next is the supraharmonic component, which we were saying. And as we said yesterday, the supraharmonic component is between 2 kilohertz and 150 kilohertz. This is said to be the supraharmonic frequency. So below till 50 hertz, till this 2 kilohertz, they are said to be the lower order harmonics. Okay, so the mainly here we are seeing the supraharmonic component. So we did a measurement with many different vehicles. Around 4 or 5 electric vehicles were brought to the laboratory, and the data was taken. And that from that data, like it was a home like setup where there was a home. It's said to be Sarah's home. So there the LEDs are there. Solar is powering that home, and EV is also connected. And so in that conditions at the PCC, different measurements were taken. So and at the EV end also measurements were taken. The protective and like neutral and protective earth also the measurements were done, and that is shown here. So you can see that at the EV end, if you see, this is the component which you can see. Okay, and mostly around 6 kilohertz ki ek band you can see here, a narrow band of 6 kilohertz component. Okay, so this is the frequency domain, this is the time domain, and this is frequency and time domain. So that component you can see throughout it is present, and same component at the PCC also, that component can be seen. And similarly the component can be seen in the protective earth also, neutral and protective earth. So this one which is moving in the neutral and protective earth, it is said that this component may result in the RCD tripping. Okay, so it may cause an RCD tripping. So how to measure this? If you see with the data, I can just show you if time permits, because till 10:30 I have time. Otherwise, tomorrow morning also half an hour I'll be taking until the expert joins, so you can see at that time. Okay, so this is the thing, and like this is another vehicle, and this vehicle who brought this car, he had a complaint that when he charges his vehicle, he could see some flicker in the lamp what he is using. And then we did the measurement for that also, and there you can see that there is a like a band. This is the band which can be seen at around 45 to 50 hertz ki ek chota sa band, like band of frequency could be seen. So this was a switching frequency of the electric vehicle, that is the power electronics which is used there. So that component was found. And when at the PCC, there was a very different phenomena seen. That might be that is what is creating this light flicker. There you can see here an intermodulation can be seen, like an intermodulation with the supply voltage with a phase shift of 180 degrees. So this is the supply, and here a phase shift or something like this can be seen here at the PCC. Okay, and apart from that, there was one more component of 100 kilohertz, but that component was found in all the vehicles. Here you can see that component. Similarly, that component is seen here also. This is another vehicle. So then we came to conclusion that that component is actually not because of the vehicle. It is from the upstream. Might be something connected in the laboratory is creating that component. Okay, so this is one of the study. Okay, with the same study we were telling like there is a possibility of RCD tripping. So first of all, a simulation based study was done, and after that we did a hardware based thing also. Different RCDs, type A, type B, type C, different RCDs were taken which were used for different applications. And in that also the supraharmonic component was just pushed in, and it was studied whether it is tripping at the same instant or not, whether it is blocking. So we saw a different phenomena there also when hardware was done. So first of all, as we all know, before going into the hardware based study, we do the simulation. So in that simulation, a MATLAB based model was taken. So this is the supraharmonic component of that same electric vehicle which we saw there. So sorry, no, this same component was taken for simulation study. It was this was the thing, and you can see that component here, and that was injected into that same data was taken. That same data was taken, and that was injected as in like electric vehicle injection, because that was created by the electric vehicle. So this was an electric vehicle model, because these supraharmonics are more sensitive to capacitors. So only a capacitive model was taken here, and this component, that value which we got there, was injected into this model of the grid, and the measured leakage current was measured here. How much was the leakage current? Okay, so that was done, and then that current was taken, and an RCD model was made using a summing transformer model was made with an electromagnetic relay. Okay, and in that case, first of all, only the supraharmonic component was injected, and after that, the primary current of the RCD was also excited. So it could see that when the primary current and the supraharmonics is there, there is high value. This is the set value. Primary current setting is this. So if the value goes above this, then a tripping may occur. So you can see some values here which are above. Some values here which are above the set value. So there is a possibility of tripping. So, and for same thing, the magnetic force was calculated, and there also you can see that when there also it could be seen that when there it could see that when this is the supraharmonic component, this is supraharmonic with the primary component, and there are play times where it goes above the set value. So there is a chance of tripping of these RCD, which are unnecessary trippings. Should not occur, but false tripping. Many times we have seen when we go and put some things, it trips. So like might be when we are charging something, an electric vehicle or something, the nearby thing, or when we are switching on a particular like oven or something, it trips. What is like the RCD may trip? So what might be the reason? So in our laboratory also, when we do with the multi-level inverters, when we turn on the switch of the input supply, automatically it trips every time, and then we have to go and rectify it. So what might be the reason? So in such cases, you can do the measurements and see, is there any other component which is apart from this inrush current, or apart from any fault. It is actually in our laboratory, it's not fault. When then what we do is again and again, twice or thrice when we do, then suddenly it gets stuck and it goes. So it is not because of an inrush current, or it is not because of this. It may be some, whenever we use power electronics, then might be it is because of some other component being superimposed into it, which is making it go above the particular value. So there may be reasons for it, because we are not studying it, so we are not knowing it. But in such cases, we can do such studies and see what are the problems. So this is also a thing which was noted. So when in blogs and all, people write, when I do this, this is occurring. So that gives you an idea that yeah, this can be a problem. We can take up, and then we can do research in that. Okay, so this was another work which was done by Selshuk Sarkar with like Sara and Math, and this was published in IEEE Transaction on Power Electronics also. A very simple work, but very valuable work, you can say. So you know that in case of a LED, you have a rectifier. Okay, and there is a rectifier circuit, and beyond this, there will be a chopper based circuit like a MOSFET or IGBT or some like some circuit based, like some power electronic based chopper circuit is there, which will chop this AC voltage, like AC current is first of all converted into DC here, and then after that it is chopped. Okay, so once it is this DC value is chopped, a reduced voltage we get here, and that is in term here you can see LEDs are connected, light emitting diodes are connected. Okay, and series of such diodes are connected here, which will emit light. Okay, so here in this case, what happens is, along with this AC component, if supraharmonic component is present, high frequency component is present, superimposed on this, in that case, say for example, if when it is diode conduction, here you can see when diode is conducting in normal, it is like this, it has to conduct like this. Okay, so this is the diode conduction period. During that, this is the modulation depth, you can say, that is the brightness, or you can say it is the brightness of the lamp. Okay, the modulation depth here in terms of brightness we can tell. So this black one or this blue one which I'm drawing is the actual value. When the supraharmonics is injected into it, you just think that this is a component, this is a high frequency component. So in this case, around 12.5 kilohertz component, 12.5 kilohertz component is superimposed on that. So and magnitude is, first they have kept it as 3 volts. So in that case, you can see here that this is the permanent conduction period of the diode. Diode is permanently conducting here, and these are said to be the intermittent conduction. The sense here you can see these are intermittent conduction. That is, it's not fully conducting. Okay, in the, like some portion is getting cut. So this here in this case, if you see, this is the intermittent conduction period. Similarly, here it is the intermittent conduction period. Similarly, for the same experimentation with 12.5 kilohertz, and this magnitude is increased to some 7 volts. Then you can see that this is the permanent conduction period. Okay, this is the permanent conduction period, and this is the intermittent conduction period during that time. So you can see that when this magnitude of supraharmonics increased, the permanent conduction period of these diodes has decreased. So automatically what happens? The current flowing through this also will decrease. That is and automatically the illumination of these LEDs. So the modulation depth in first case, you can see the red here. And then in this case, you can see it has reduced much. So this is also a reason like why light is flickering. Okay, when supraharmonic component is injected, the diode conduction period will decrease, and as a result of it, when the diode is not fully conducting, automatically current going to the other end is less. So automatically the brightness will reduce there. So such things, these are very small things, but by analyzing it, you can understand, you can infer a lot of things from this. Okay, so this is also a thing. And next, coming to this, what are the other problems that can be caused by this supraharmonics? Even though the magnitude of supraharmonic current is low, so that was a thing somebody was asking yesterday, that ma'am, the magnitude is less. Yes, the magnitude is less. They can get superimposed on the background emissions while they are propagating through the protective earth and risk the RCD tripping. They may cause the interference with lighting, which I showed you now. They may cause also audible noise. You can hear some audible noise when these are working. And for us, might be it is okay, because if for us, we are the range which we can hear is some 20 hertz to like 20 kilohertz. Okay, but a normal human being, from 20 hertz to 17 kilohertz only we can hear, like us of our age. But when they are a kid, kids and old people can hear between this range, 17 kilohertz to 20 hertz. Kids and old people can hear. So you just think you are charging the vehicle, might be the child is crying, or an old person getting more aggregated, like aggravation, or he's getting angry. The reason might be that he like, because of such things what he can hear. Or if they're dogs can hear from some 40 hertz till 40 kilohertz. Okay, so this range. And cats till I think 60 kilohertz or something. So bats even higher range. So even dogs may get aggregated with these harmonics. So like these are also like very sensitive studies which we have to do. Like is it really causing some problem? So now many people are doing study in this. That much study has not. So if this is a problem, automatically immunity limits has to be set for those devices. So standards are required for it. So that's why many studies are going on in this area also of audible range. Okay, and then it affects the quality of the voltage, that is also there. It may affect the interference with communication lines. So that is also a problem which we can see. And another thing is, like yesterday we were talking, actually the number of participants, yeah, now many have joined, so I can just show you. Actually, I took those papers and kept, but since the number of participants joined at that time was less, I thought like so. This was the thing which I was telling you yesterday, that a cable failure had occurred in the Eagle Pass installation. This is in Texas, the Eagle Pass installation. So there, an installation was done by this ABB Eagle Pass, a back-to-back converter-based back-to-back installation at Eagle Pass by ABB, EPRI, and AEP field demonstration, and for a recent project was done. And in that case, you can see that the voltage source converter base transmission controllers, which use gate turn off switching components, introduce new type of voltage, high voltage stress. So there was some high voltage stress introduced on the insulation system. Okay, and the materials, the fast switching. So there, the main thing that what they found was a fast switching component like IGBT may generate or cause high frequency voltages. You can see that high frequency voltages which are superimposed on the power frequency. So these components get superimposed on those, and it creates a high frequency voltage component and insulation within that station. So the insulations within the station may thereby be continuously exposed to some new type of voltage stress. So those insulations were coming across a new type of voltage stress of which it has not been designed or tested. So those installations were not designed for this, or it was not tested for that also. The high frequency voltage may, under special circumstances, cause insulation damage and magnitude level which are well below the dielectric voltage withstand at power frequency. So compact insulation system with resistive and reactive grading of electric field are particularly critical. So in this case, again, several compact type cable termination rated 24 kilovolt with resistive and refractive stress grading have failed in these. 1 second, the next expert is calling, so let me just I'm sorry, like actually expert, he just want to confirm that he's joined because I just told him yesterday. Can you see my screen? Did I remove the thing? Can you see my screen? Please, somebody can confirm it.
Yeah, madam.
Yeah, thank you. So here you can see several compact type cable termination. So the place when we were doing our research also, they brought a cable termination failure, and they were asking might be what are the reasons, and they wanted to do some measurements there to see that what is the reason. Okay, so these are high voltage components with high insulations there. Still these components, because of these low magnitude of supraharmonics, and here you can see continuously three terminations. When I was reading somewhere, I could find that there were three such failures, and it was like repeated, like within some few days itself, these three failures of cables occurred. And then they measured all the things, and they were noting it, and they found that it was due to this high frequency component which was superimposed on the fundamental component. So this such big problems can occur. Okay, so you can just go to, this is an IEEE transaction and power delivery paper. So this problem is seen in many places, but since this were not under our radar, we can say we were not thinking that these will create such problems, or the problems what are occurring, they couldn't correlate it before. Now in many places when they correlated, they could understand it is because of such things. And this is also a paper, measurement and analysis of superharmonic influence in MVLV network containing renewable energy sources. So this was a measurement done in Germany. So this was the plant MVLV network, and you can see here a low voltage PV panel. Might be this is a panel in our institute in the top what they have kept, and almost 15 kilometers apart. Again, there is a low voltage plant here, and again there are wind plants also. So such a place they did the measurement. So they you can see MP1, MP2, and MP3. The measurements were done around 15, 16 kilometers apart, and they could find this supraharmonic component around 16 kilometers apart. Also, the switching frequency of these converters were found here. Okay, so it was the same component which was found on the other ends also. So then it was identified that these components can propagate through kilometers and might be there if it superimposes with another component and some resonance is created that may result in many problems. So these are some of the practical things already in literature. So if you are looking for such research, you can just go through. I wanted this one and sorry. Yeah. So these are the different problems what supraharmonic can bring. Another thing is the light flicker itself, a study which we did in that these fast voltage fluctuations, say whenever there is charging, yesterday also I showed before charging there is some checks also. There may be some like voltage checks or insulation check or onboard battery protection check, CAN communication check. All many checks are going on in between these vehicles when it is charging. Because of that, also there are some fast voltage variations. Okay, when these fast voltage variations occur within a 10-minute interval, within 10-minute interval, if these fast voltage variations occur, and depending on the magnitude, like how big it is and how closer they are occurring within this 10-minute interval, light flickers can occur, because light flicker is usually measured for 10 minutes interval, and the value is given in by PST. We say it as PST. That should be less than 1. PST value should be less than 1. So if say you have 100 people, or like from 100%, even 50 percentage of the people can see that some, they can perceive that there is some change in light, then we say that the PST value is greater than 1. Okay, so it is something what we visualize. Say you are in a room and you are doing some work, and after some time you feel that you are feeling giddy, or you feel vomiting sensation, nausea or something. It might be because of the light which is above you, the LED lights. Actually, when you see nothing, you cannot see anything, but might be there are feeble slight variation in the light intensity that is creating all these things, but all will not feel that. Out of 100, maybe 50 people person can feel that. So if 50 people are feeling it, then we say that the PST value is 1. So usually with human, this experiment conducting is very difficult. So you have photometers. Using that, you can identify these values. And mainly the magnitude of these components depend on many things. As I already told you, it depends upon the magnitude, like it depends on the charging station current of the charge. Is it a 16 amps charging station or 32 amps or 64? How much current it is drawing? Based on this, the magnitude, say higher the current drawn, the magnitude will be higher. In that case a bigger drop you will get. So one is the charging station's current rating. Then it depends on whether the grid is weak or strong. I said when our grid is far away from the transformer, the impedance will be high and voltage drop will also be high in that case. So if it is a weaker grid, then the magnitude is still high. So more the magnitude and more closer these drops, in that case you can see a light flicker. So such an experiment we did. So here you can see these are the EV1 and EV2 charging, and the voltage drops and the current spikes are just marked here. And in that case, with this reading, we just took the voltage and current reading. And we just did the scatter plot. Okay, the scatter plot gave this slope also. So from this slope, we found what is the impedance of this. So it was almost all the three phases. We got 40.8 milliohm. So that is said to be a stronger grid. So in that case, with the amps, it was drawing around 47 amps. So you can say that the voltage drop in that will be around 1.92 to 2.07 ka voltage drop in that line can occur. Okay, so this was a general thing taken from that data. Here also, yesterday's measurement also I was showing you, lot of these drops are seen here, but it was not due to the EV charging, because we could see that when EV is not charging also this is something from the background. Okay, so again they are doing the measurement in order to identify what are these drops. It cannot, it couldn't be, and these are only small, around 2-3 volts ka drop. But what caused this? That also was identified. This was the electric vehicle, um, uh, like when the electric vehicle measurements was taken, these drops were seen. Okay, and now in order to do this experiment, two networks were studied. One was 83 customer network, and the impedance of this 83 customer network, the transfer impedance was found. So from that data, it was found that the transfer impedance was varying from 0.0496 to 0.3512. So this was the impedance of the grid. So with that component, like, and you know that an electric vehicle will draw amps from 1 amps to 16 amps. That is, so for with this impedance value, this was multiplied, and it was found that around 5.5 volt drop can be seen, and might be 3.5 volts could also be seen of a drop. Okay, and this was said to be a strong grid. The value 0.04 to zero point 0.3, it is said to be a stronger grid. And that strong grid can give a voltage drop for 16 amps till 5.5 volt. Okay, and similarly, in order to get a weaker grid impedance also, what we did is around 60,000 customer network, we say this, there is 59,468 customer network was taken, and their impedance was also taken. The transfer impedance of such a network was also taken, and that value was a very small percentage of value was between 0.69. So this was a weaker grid. Okay, so this had strong grid components, medium grid, as well as weak grid. So we want to know for a weaker grid, what is the impedance. So for that only, this customer network had both weak, medium, as well as strong grid components. So for the weak grid, the impedance was around this. For this component, again, when 1 to 16 amps was multiplied with all those different impedances got, and it was found that this weak grid can give a voltage drop of around 11 volt. When you're charging an EV, like strong grid can cause a voltage drop between 3.5 to 5.5. A medium grid, again, I think 7 point something or something, and a weak grid can give a voltage drop of around 11 volts there. So in such a thing, a probability-based study was taken for that 83 customer network, thinking that in that 83 customer transfer, this is a transformer which is having 83 customers. So in that, we are just assuming only three EVs are connected to that customers. Out of 83, only 3 people are using the EV. And similarly, 4 people, 5 people. So until like 80 people are using this, what is the probability of getting that step in the voltage? Okay, that we saw that when we are charging, there are some steps occurring, is it? So these steps, what is the probability of getting these steps? So it was found that in that 83 customer network, if 50 people are charging at a time, there is 100% probability that you may get greater than 4 drops in a 10-minute interval. Okay, so because PST we calculate for 10-minute interval, then only we can see the light flicker. Similarly, there is 96% probability that greater than 1%. And if the 80% are doing, then that is 100%. 80 people are charging their EVs, then there is 100% probability that for greater than 4 or greater than 10 flickers, sorry, not flickers, fast voltage fluctuations can occur. So the same study with those things, like a measurement was done where lamps were LED lamps of 32 different topologies were taken, and a photo detector was used, and that component that like within that 10-minute interval, the number of spikes were just introduced into the grid, and this was the device under test, that is a equipment under test, we write it as EUT. This is EUT, where this lamp with a photo detector around 26 centimeters apart was kept, and this light was detected, and through lux, like with a lux meter, this again the data was taken to the computer to analyze it. So it was found that this is, say, the PST value should be less than 1. We know that. And this is for strong grid, medium grid, and a weak grid. And this is for consecutive drops, and this is non-consecutive in the sense, say, in a 10-minute interval, this is a 10-minute interval. Consecutive in the sense, let us assume that these drops are occurring continuously. Non-consecutive in the sense, we are just assuming that it is like occurring at different intervals, not very close. So both were determined. Okay. And in that case, when 4 drops are occurring consecutively, one above the other, then it was found that some topology, this is a topology with active filters. Okay. This is a that is active topology, and this in there power factor correction, active power factor correction circuit is there. So this LED3 is an LED with a capacitor for changing the intensity of the lamp. So the different topologies like that was taken. The topology which has power factor correction circuit, that you can see that if it is a weak grid, there is 100% probability of getting a flicker. In a medium grid, around zero point 0.6, so slightly you can see. And similarly, this is for 4 drops, but 10 drops if you take, you can see very high values here. Also in a medium grid also you can get these flickers. Even in a strong grid, there is high possibility of seeing these things. And this is not consecutive, like very far also, if it occurs, there is high probability in a weaker grid to get drops, like, so to get flicker. So the inference which was drawn was, if there are many steps, in the sense in 10 minutes interval, more number of steps, weaker the grid, and those steps are closer together than it is far, when it is closer, okay, the PST value will be greater than 1, which can give a flicker. So that's a very prominent thing which was done in this study. And the flicker due to EV charging depends on the number of EVs connected, the topology of the LED lamp used by the customer, and the impedance of the grid. Okay, so how many number of EVs are charging, and the next is what type of lamp you are using. It is not affecting all the lamps. The simple lamps, it's okay, but nowadays high-end lamps are coming with power factor correction circuit, with automation, where the light intensity changes, light color changes. So many other components are used. So such lamps are affected in that case. Okay, now one more study I can just take up. We have 10 more minutes. So, like, this is an electric vehicle hosting capacity study of distribution network based on ambient temperature. Okay, so in this study, I was telling, say, there is a transformer, and how many number of electric vehicles can be connected to that transformer. So, how will we do that? So, what we do is, usually what we do in that area, what is the load of the transformer? We just take that. So okay, so this is the loading profile which of that area. This is a network of Umeo's city we had taken, and in that it was studied that this was the load, and this is for the 12 months, the January, and mostly in winters, sorry, in summers the load will be less, and in winters again high. And this is during a day, hours of the day. You can see here, if you see the, it is slightly, it goes like this. Okay, so the peak is during the evenings, and even in the morning hours, and it's something like this. Okay, so, and generally when you want to find the hosting capacity is a maximum capacity, current capacity of the transformer, minus how much loading is done. So that difference, okay, what is the maximum loading capacity of the transformer and how much load is done, so that difference will give you the hosting capacity. That is a general thing. Now, with the other effects, you can do the hosting capacity with like when the temperature is changing. So this study was based on temperature. We say that when the temperature of the when the atmospheric temperature is minus 30 or 40 degrees, 40 degrees in the sense I said in the south and all, when the temperature goes 40 degrees, the current, like the battery gets discharged faster. So the transformer loading, if you see, is more during extreme winters and during extreme summers, because the battery gets discharged faster. So you have to go and charge there more times. Okay. So the loading current, and it is an optimal and 20 degrees. In 20 degrees, you can see that the battery will not get discharged faster. So you can run for a longer time. Like for example, say yesterday I was telling you, we did it based on that data. The Nissan Leaf data was taken for this. The Nissan Leaf Karma data was there in the website. So that data was taken, and in that data, it was the Nissan Leaf around 120 kilowatt ampere hour battery was used there, and it was giving around, I think, 200 kilometers or something. So a calculation was done that on an average, a person will travel in Sweden. This is according to the Swedish data. It was taken on an average. He travels 30 kilometers a day. Okay, so considering that, like say it is 150 kilometers. With one full charge, you can go till 150 kilometer because of the extreme road condition or something. So here in this case, if he's going for 30 kilometers every day, 4 days once he has to charge. Okay, that is in a normal 20 degrees temperature. 4 days once he has to do. But the same thing in winters. In winters, what happens is when he's doing charging 4 days one, there he has every second day he has to do 2 times. He has to charge his vehicle because battery gets discharged faster in winters and extreme summers compared to the normal temperature. Okay, so based on such a study, coefficient was temperature coefficient based on the temperature of the Umeå city also. So Umeå city, you can see here, in winters it goes till minus 20, and then in summers till 20. So in summer it is a good situation there in Sweden, and again during the months December, again it goes like this. So this was the temperature of the city. So based on that, a temperature coefficient on the Nissan Leaf data, and this temperature was taken, and that temperature data of this temperature data which you could see here. This temperature data which you could see was substituted here each time in order to find the coefficient. Okay, and this coefficient was found from the Nissan Leaf data, and that was introduced here. Okay, so now this hosting capacity is not the normal hosting capacity, it is the hosting capacity along with the temperature coefficient. Similarly, if you want, you can add the harmonic component. What are the harmonic components it's introducing? So because of that, is there any decrease in the hosting capacity? So many other, whichever other factors you feel can be added as this coefficient in the denominator to find the hosting capacity. So such studies can also be done. Okay, and it was found that here in this case, you can see this is the normal without any temperature coefficient introduced. Around 1,000 vehicles can be charged under that particular transformer. It was in megawatt. Megawatts. So like, let us see here. It was 800 kVA transformer. Okay, so it was an 800 kVA transformer. And these are the MVA transformers. 30 MVA main transformers was 30 MVA transformer. So this study was done under this transformer only. Sorry. The study was done for this transformer only. Okay, for this transformer, this data was taken. So, combining all these, like here 96 customers, 241 customers, all these things added together. Some customers were the industrial loads also. So accordingly, it was seen that around 1,000 people can charge in the winters, and like 100 and 1,200 people can charge in summers, and again in winters also like this. But with this temperature coefficient, it has reduced to around 30% reduction is there. You can see here this percentage decrease, almost 30% decrease is there during winters. So during winter, around 30% less loading can only be done in the transformer. So this was actually required for the operators there. They wanted to know, because now the EV capacity is increasing there. So they want to know how much can be allowed. So based on that, because they install these charging stations for all the houses also. So how many is possible? Based on that, they required the study. So for that we did this. By introducing temperature coefficient K, there is an around 30% decrease in hosting capacity during colder months due to fast discharge of battery. Okay, so with this EV charging pattern of this, tomorrow's lecture I can just cover it. If you have any doubts, you can ask, because now our next expert will join from Opalati. He will give you a basics of these battery management system, then followed by like again a sir from Opalati. He will be doing the next session. Okay, so now I is the expert from Opalati joined? Sir is there? Okay, and if you have any questions, you can ask. Yeah, last day PPTs I'll do, because yesterday I was fully engaged. Morning session was engaged. Afternoon also I had a lecture in my master's class here. So I was not able to do it. Today surely I will do that. And I think Gopal is also there. And Gopal, have you downloaded this yesterday's recordings? So in that case, please see that we share it with the participants. I'll give you the mail IDs. Okay, so once this next lecture starts, I'll try to download all the mail IDs and I can give it to Gopal, and he can send you this recordings of yesterday, and PPTs. I will collect even from like Ajay and my lectures together. I will be sending you. We will put it in the drive. That will be done. You need not worry. Any other doubts if you have, or anything you want to ask, you
Hello,
can
madam.
ask. And one thing is,
Hello.
this lecture will be continuing from 10:30 to 11:30. Okay, and after that, you will have a 15 minutes break, and then again, Opalati lecture will start. Okay, yes, sir. Colin, sir, you have any doubts?
Uh, please, can you give me the details of the kind of instruments you use for making the measurements?
Yeah, say actually you can use any type of power quality analyzer. Okay, in Sweden we use Hioki. Okay, and Yokogawa is also we have used here at Nitra also we have Yokogawa. Now we are going to get a Fluke or Hioki based power quality analyzer. But when you get these power quality analyzer, usually they are for 50 to 60 hertz resolution. Okay, so here when you want to measure the supra harmonics of 2 kilohertz till 150 kilohertz, 150 if you want to measure, then 300 kilohertz sampling should be there. Then only, say, according to sampling theory, only half of that can be analyzed. Okay, so for 150 kilohertz till 150 kilohertz you want, you have to minimum go for 300 kilohertz sampling frequency based power quality analyzer. Or like mostly 300 kilohertz I have not seen in any of the companies. 500 kilohertz are there, that is best. So you have to go for power quality analyzer. Many power companies are there. Yokogawa is there, Hioki is there, you have Fluke is there. So anything you can go, and you can go for these frequencies. You can just check it out. Any other doubt?
In that case, if we don't have a power quality analyzer, it means we cannot carry out these
Yeah,
measurements.
it is difficult, but still, I think once I have shared, there is a PQ meters website where the PQ meter throughout the world, wherever they do measurements, they put it in the website. So there also high frequency components are measured by different like industries as well as institutes, and they have put it in the website. So I will once I shared in one of my course, I have to search for the link. So I can share that thing. So I think PQ meter, if we search also, we may get it. So there are websites where these data are shared. If you don't have it, then that is the only possibility. But there will be limitations. Say, like if you want for you want to study a wind power plant, or you want to study a solar, or you want to see it for the data center, or you want to see it for the electric vehicle charging. So in that play case, you cannot expect that people will put all these data. Okay, so
Okay,
that's the
thank you,
thing.
ma'am.
Yeah, so yeah, getting data is little difficult. You should have. So now also we are in the process of procuring. We have a Yokogawa. So inside our institutes, in a solar plant and other thing, we are trying to take measurements. But apart from that, if we want to go and in the field, we want to take EV measurements, where because we have number of electric buses introduced in Chandigarh. So we are trying that in case if we can contact and get those datas, that will be good. So for that, we are trying to purchase a power quality analyzer. Uh, so now the tender and other things will go. So if you have that, that's why I said this. Such forums, many of the institutes, if you have power quality analyzers kept in the almaras there without any measurements, if you can bring those things out, and with such a forum you can create any space where you can put data, and people here can contribute. Like in case with your data we can analyze, we can put your name also, because you're giving us the data, we can put your name in the research. So that's why such forums are very helpful. It is not only knowledge sharing, it is research. We can identify research and work together also. So that's the main thing we want, because many people don't have data, but they are willing to do research, or many are there who don't have time to do research, but they have the data. So those peoples can come together, those who want to work with EV, or those who want to work with data centers, or those who want to work with renewable energy sources measurements. This is possible, because what I can see here is many of the institutes now also, when I was talking with somebody, they said, yeah, we have it, ma'am, we had not used it. But again, we have to see whether they have that possibility of measuring high frequency components, because otherwise, let's say if you have 50 hertz to 60 hertz also, you can go for interharmonic studies of EVs. Interharmonic studies at 3.5 kilohertz, or you have 11.8 kilohertz or 15.3 kilohertz. These, sorry, not kilohertz, hertz components present. In that case also, interharmonic studies are possible with those power quality meters. Okay. Any
Thank you, ma'am.
any other questions or any other doubts you want to clear? Is our expert from Opalati there? Has sir
Hello, ma'am.
joined?
Let me ask one more question.
Yeah, yes, sir.
Hello, good morning, ma'am.
Yes, sir. Yes, sir.
Samir Singh
Samir,
from.
okay, Samir, sir, hai. Sir, very warm welcome. One participant is having a doubt. I'll clear that, and then I'll hand over the session to you, sir.
Sure, ma'am.
Yeah, who was the participant, sir? Please ask. Colin, sir.
Yes, ma'am.
Yeah.
Uh, after you find that a certain um, maybe EVs sending harmonics into the system, what was the solution?
The
Did you
solutions
find
are,
any?
yeah, I
Uh,
understood your question. Say the solutions are now, till now, this was not identified. Now, the committees, even the IEEE and all the other committees, they are trying to set up standards so that immunity limits can be set up for these converters. Now, a manufacturer, now they, according to IEEE 519 standard, they check all the lower order harmonics, and some of these like higher order harmonics, they have to reduce. They put a filter, or they do some type of switching logics in order to remove it. Now what will they do? Now these supra harmonic range will also be specified that this cannot be there. So they can design any filter. That is up to the manufacturer how to eliminate it using some filters, because these are all high frequency component. Even with a small filter, this can be filtered out. Filter design for high frequency component is not so tough. You can do that easily. If it is lower, then you have to go for some selective harmonic elimination technique, or some techniques you have to use. So that is a scope here. You can come out, if you can come out with a new method for eliminating these harmonics, that's well and good. Okay, sir.
Okay, thank you.
Okay, thank you. Thanks for the question. And now I just hand over the session to Samir, sir. He's from Opal RT. And I first of all thank, because within a short notice, he had come here to deliver a lecture on the battery management. Because yesterday's session also, many participants were asking on this battery management, and it was not my area, though a little thing what I had given. So that's why we had called you, sir. Thanks for accepting our invitation within this short notice.
Thank you, ma'am, and thank you all. Good morning to all of you. I'm not expert on BMS, but we have been using it from long time, and we are the provider of a real-time simulator, so which is used for battery management system validation. Okay, so based on my experience, I have captured a few presentation slides, so which I will be sharing to you, and we can discuss there. So I'm going to share my screen. I hope my screen is visible to you.
Yes, sir.
Okay, thank you. So my topic of presentation here is real-time simulation based testing and validation of DMS for electric vehicles. Okay, and here we have some points which we are going to discuss in this presentation. So first is basics of BMS, and the second is BMS design requirements, BMS features, BMS architecture, cell balancing, state estimation, real-time simulation, HIL testing and validation. And then we'll follow up with some questions. We'll discuss on that. Okay, so now to start with the battery management system. So what are the system requirements? So why battery management system is required in electric vehicle application or battery based energy storage system application? Okay, so the first most important point is to provide the protection from hazardous. So it provides the safety of operators for the a person who is using battery powered system. Okay, so this is the most important point. So BMS role is to provide the safety of operation of a battery based system. Okay, so it has to detect unsafe operations, and it has to isolate the battery high voltage battery power system from the load, and provide some indication to the operator so that he can follow some safety precautions. And the second is to provide the cell safety of the battery pack. So the cells are inside the battery pack, so the battery is going to be a very huge size and a very high capacity battery. In that there are number of cells connected in form of some topology series and parallel combination. So it has to provide the safety of cell and analyze the failure cases, and avoid the damage of the cell. So it has some software based control and some hardware which is going to be connected with the battery, and then it detects the failure condition and to protect the battery cells. The third is the prolong the life of battery under normal operating case. So this is
So can you
also
go into the presentation mode?
okay. Is it not in presentation mode
No, no, sir. It is in the slide mode only. And it was not shifting also, yeah.
now?
Still, it is in the normal mode, like it is not in the presentation mode.
Okay. Is it better?
No, same. I think did you share the full screen or only yours?
Okay.
You have to share the full screen. At that time, you will not be able to see any of the participants or anything. But
Okay.
I think your slides were also not shifting.
Is it better? Okay, let me check my net connection.
Net connection and everything is fine. I think when you are doing the presentation, sir, your
Mhm.
entire screen, that option is there.
Yeah, I did that, but I don't know why it is not working to you.
If it's not working, then you can just click on that slides also because the slide was not moving. It was in the same
Okay,
position.
okay, okay, okay. Wait, hold on. Here it is. No. Is it better? No.
We could see, but it is the same. It is not in the presentation mode. We could
Okay,
see your slides in the left side.
okay. 1 second. What?
You can press F5 for presentation mode.
No, I'm in presentation mode, and I'm not sure why you're not able to see in presentation mode. Slides are also not moving.
Sir, it was not moving, but you have to just select it, then it will move. You just select, that is enough. And you can left side, you can just make it very small. That left side slides, which we can see, move to the left, so it will become very small, so that we can see your slide little more bigger.
Sir, you need to share your whole screen.
No, he's doing it. I think some other he's
Should I
sharing the
should I
screen.
rejoin? Should I rejoin?
No, I don't think so, sir. It is not that problem. Well, it's not a problem. You can take it. We can see your slide, or maybe your
Is it better?
now you show it, sir. Now you are in the full presentation thing only. Now you go and open your PPT. Yeah, do the present. Now we can see it, sir. Now it's correct. Now it's correct. Yeah, we can see. But you will not be able to see us. That's not a problem. You can tell in case if it is getting cut, I will just inform you.
Yeah.
Thank you, sir. Thank you.
Sure. Thank you. So yes, so the first point was that to protect the safety of operator. So that is most important point and the most important function of BMS system. And the second is protect the cell of battery. So there are cells inside the battery. So BMS has to make sure that cells are working properly. They are not damaged. They are properly charging and discharging under the controlled way of functioning of the battery packs. So there will be hardware and software which will be working to control the charge and discharge of the battery pack. The third is prolong the life of the battery under normal operating case. So this means that the role of BMS is to monitor the battery cells and estimate the functions of battery like SOC, SOH, and the aging effect of the battery. So during charge and discharge, battery getting aged depending on the number of charge and discharge cycle. So it has to monitor the battery states and with some control algorithm, it has to estimate the battery life each time when it is charging and discharging. And the fourth most important point is to maintain the battery pack in a state. That means it has to make sure the battery pack has some SOC label so that the battery is functional and connected with the system. So there are there is charging and discharging process of the battery. So in that case, the BMS has to make sure the battery is charging properly and discharging properly, and it has some minimum or the battery SOC level, which ensures the function of full system, full vehicle with the battery, and battery is active. So minimum functions will be required in the vehicle system, which will be confirmed from the BMS system only, whether the battery is able to support that function. So it has to make sure that minimum function is operational, or minimum function is ensured by the BMS system. The next is to BMS design requirement. So there are different aspect of BMS design. So first is the sensing high voltage control. So in this, there are different parameters again, like sensing the voltage from the battery cells, and current, and the temperature sensor. So in that, the BMS role is to monitor the voltage and the temperature and the current of each cell. So this is the one of the hardware and main role of BMS system. And the second is the protection. So it has some electronic circuitry which ensures the protections of battery and battery cells against overcharge and over discharge, overcurrent, or cells short circuit, and some extreme temperature. So this is also important part of BMS. And the third is interface. So in interface, BMS need to be communicated with the operator, with the console system, and with the hardware. So there must be some proper communication link. So some communication protocols need to be there with the BMS system, so that the BMS can communicate with these entity like operator or operator console, or some other hardware like charger, or the vehicle controller, so that it can pass on the message and the functional requirement of BMS system. And it can also alert user or operator if any problem is there in the BMS, or any fault is there in the battery packs. And the performance management is also part of design requirement of the BMS. So in this, the performance is based on the battery uses. So the SOC of battery is like a fuel of vehicle. The performance management is important, and it depends on many points. Many criterias are there, like the drive cycle of vehicle, a charging and discharging pattern, or the type of charger you are using, and the algorithm for estimating the SOC, and the complexity of the BMS circuit. So there are so many parameters. From that, you have to estimate the SOC, which increase your performance, which increase the performance of the battery and vehicle. And the last point is the diagnostic. You should have some proper diagnostic function, diagnostic of the battery management system, or battery system. So that you are able to see the performance and the fault, or the level of charge and discharge, and is there any maintenance required for the battery system or battery management system, like a state of health, detecting any abuse, or the state of life of the battery pack and cells, you will be able to see. So diagnostic is also very important part of the BMS system. So these are the main points which are required for designing the BMS, battery management system, for electric vehicles. So some of the important features of BMS are here, like battery cell monitoring, cell input output current and voltage monitoring, charge and discharge control, state estimation like SOC, SOH, and SOF, and then battery protection, cell balancing and equalization, power management control, operating temperature control, heat management, communication and networking, data storage, data acquisition, fault diagnosis, and assessment. So these are some of the important features of battery management system. And here we have BMS architecture. So BMS architecture can be a simple or complex, but the main components or hardware in the BMS system are divided in two parts. One is the controller, which is running the algorithm for battery management system. Another is the hardware, like which is connected with the battery pack system, which is a slave of battery management system. So it mainly two parts, like slave and master. Slave is associated with the battery pack or battery cell connections, and then the slave is going to communicate with the MCU, master control unit, microcontroller. So this is the architecture. As in some cases, the BMS system is going to be different, depends on the application, the type of vehicle. It can be either distributed type of BMS system or integrated type of BMS system. So if I say distributed, that means the slave of BMS system is going to be apart from the master of the BMS system, and there will be a communication link in between. And in some case, like in integrated BMS system, the slave and master both are going to be in the same hardware. So it happens usually when we have less number of cells. So you are going to have like integrated type of BMS system. And when you have a very big battery pack, where a lot of cells are there in the battery packs, and so many modules are there. So each module require the slave unit. So slave unit is going to be with the battery module, battery pack, and then the controller will be apart from that, and there will be a communication link in between. So depends on the vehicle type, whether it's a light vehicle or a low capacity vehicle, or whether it's a passenger vehicle, or very heavy vehicles like mining vehicles or excavators or big truck. So it depends on the type of vehicle. So in accordingly, the architecture of BMS is defined. And battery interface, here we can see in battery management system, the hardware and the software is going to be like this. So we have subsystem of pack 1, subsystem of pack 2, and pack 3. There are different layers, and the algorithms to estimate the SOC. So the model is running for that SOH, and the temperature monitoring, detecting and making any decision for switching between different condition, and the CAN module, which is going to be a communication link for BMS and BMS to some other controller in the vehicle. So and there is going to be an algorithm for cell balancing and controlling of the hardware, the equalization circuit, and you are going to have a battery pack connection, battery cell connection. So you are going to have different module for that, like sub battery pack 1, sub battery 2, pack 2, sub battery pack, and so on. So depending on the number of cell and the topology you have for your vehicle, so how many modules are going to be there, and how many series and parallel combination of cells are going to be there. So this is a typical battery interface with the BMS system. Now, next is the battery state estimation. So this is very important when a vehicle start and become functional. So there are different stages where BMS has to go through when it connects with battery management system. So it start with the monitoring of current, voltage, and temperature of the battery cells and the battery pack, and then estimate the SOC, and then it estimate the SOH, and there if there is a balancing requirement. So whether the battery is charging, whether your vehicle is charging, or whether your vehicle is running. So depending on that, if the cell balancing is required, it does that, and then it computes the energy and power limit. So this is one of the loop when you start your vehicle. So the BMS enters in the main control loop, which executes at regular frequency. So in each interval, it has to do this process. So it continuously monitor the voltage and current and temperature of the cell and the state estimation it does. Okay. And then comes to modeling battery cell. So this is very important aspect when you test and validate the battery management system. So battery management system is actually having a software algorithm which has to be compute your battery states or battery parameters very accurately, so that you are able to function the battery in a safe operating mode, and you are going to optimize the battery performance. You are going to optimize the aging effect of battery, and the range of vehicle is all depends on the battery the BMS algorithm. Okay, so when you connect with the battery, real battery, you are not sure how much how battery management system is responding against that battery. So to make sure, you need to have some kind of battery model, and the algorithm need to be validated first before going to with the real hardware. Okay, so the battery cells modeling is also important when you test and validate your battery management system. So yeah, to estimate the different states of battery, you need to have a battery model for that. So mainly there are two types of battery model. One is the equivalent circuit based model, and another is the physical based model. So in equivalent circuit based model, basically you will have some electrical circuit of electrical design of battery. So that electrical design is actually some kind of uh, modeling where you do some testing of the physical system and collect the data, and you make some kind of lookup table in the model, and with that you predict the predict the functioning of the battery, and you are going to have electrical circuit design for that battery pack. Okay, so this is like electrical circuit which is like fast in the response, but it may not match the electrochemical behavior, exact electrochemical behavior of battery, particular cell chemistry battery. Okay, so this is electrical circuit. It is just based on the assumption. Not only based on the assumption, you also collect some field data of battery, real battery, and you feed that data to this type of electrical circuit equivalent. Okay, another the physical based model, which is actually simulate the battery chemistry. So the reactions and the battery, different type of battery cell chemistry with the in this model you can have. So this is more accurate, but this is like slow in response when you do the modeling of this type of battery. Okay, so it may not be actually matching with the real life batteries also. So in the sense, it will be like slow in the response, and you are also not very much sure whether it is actually matching with the real battery behavior. But yes, it will capture that type of reactions, electrochemical reactions in the modeling. So yeah, it is always a challenging when you do the modeling of this type of system, battery system, or where any chemical reaction is involved. So when you compare with this modeling results and with the real battery results, there will be always some differences. But here you have the flexibility to have your design of battery cell, a particular battery cell, and you are able to validate the battery management system with this approach easily. Okay, but when you go with the field testing with the battery management system and battery connected with that, so you may not be able to perform as many as tests which you can perform by having the model and by having the algorithm in the software environment. Okay, so that's why this is very important to have a battery model so that you can have number of tests performed with the battery management system. Okay, so this is another point, SOC estimation. So SOC is going to be a very important point for battery management system. So because this is going to impact on each functions of battery and battery management system. So one of the important point is longevity, and the second is the performance, and then reliability, density, and economy. So longevity of battery life, SOC defines that, and here the estimation of SOC can be done from different approach. There are different techniques. So whatever technique you follow, it has each techniques will have its own advantage and disadvantage. In some technique maybe the simple, and some technique may be the complex. So simpler is the technique, less cost is involved to implement that, and the complex is the technique, more cost will be involved, because this will not only have the software algorithm, this will also be associated with the hardware architecture. So the circuitry involved in the BMS system also plays very important role in estimating the SOC. Okay, so SOC is actually depending on so many variables in the BMS architectures, at software level, at hardware level. So longevity means you have to increase the cell life, you have to increase the battery life. So SOC, you estimate the SOC correct, and then your other function will start. Your operator will get to know how much SOC is there in your vehicle and how long it can run. So that SOC defines the control of the battery pack, and vehicle. Okay, so if you correctly estimate the SOC, you are able to operate your vehicle in a safe operation. You are getting good performance from your vehicle. You are getting good range. You are taking care of the cell life and the safety of the battery pack. And then the next point is the performance. So performance, of course, again is the same thing, like performance means you are optimally using your battery. So that means the charge available in the battery you are optimally using. So whether is irrespective of different cell behavior, whether it is charging fast or discharging fast, or whether the cell is weak or cell is strong. So with respect to these conditions, if you are able to get good performance, that means this is very important when it comes to SOC estimation. So like taking care of the cell life, and then reliability. Reliability means how reliable your battery is. So it depends on the SOC, how you estimate it. So if you incorrectly estimate the SOC, that means you are operating a vehicle with respect to that SOC. But that SOC is calculated whether it has been taken care, the safety of the cell, whether it has been taken care of the charge and discharge pattern of the battery cell, whether it is addressing the cell balancing or not. So it all depends on the SOC. So vehicle, check the SOC, and it looks like a fuel of vehicle. Okay, I have this much of SOC. Now I can go. So reliability is depending on that. So how reliable it is, whether the vehicle is going to be running for a year or 2 year or 5 months, 6 months. So reliability of any system depends on this estimation. Density. So density is again a very important point here, because the size of battery pack is going to impact on the cost, is going to impact the vehicle type, whether you are going to have a two-wheeler, three-wheeler, or four-wheeler, or heavy vehicle. So density if you have very good design for the SOC estimation, you are optimally using the cell for battery performance with a smaller area size of the battery design. Okay, the density is that means, if you have for example, if you have 10 cell and you have SOC estimation from that, and you have some ampere hour rating of your vehicle. Okay, and now suppose you have 8 cell, but you are getting same ampere hour rating or same SOC level from that battery pack. So that means with high density, that means the precise design or compact design of the battery pack, and you are getting good SOCC and performance and reliability from the same thing. So density is that, and then economy. Of course, if you use less number of cell with the good performance, with the good reliability, with good longevity, the economy is also there. That means your the system will be economical. You are not using any bulky design or bulky battery pack. Uh, and you are not using so many cell of driving the same system, so it will reduce the cost also. So this is very very important if your BMS algorithm is able to do the SOC estimation correctly. Yeah, and the next is that the SOC, the algorithm is depends on so many parameters of the vehicle. So this is the drive cycle. So that it depends on the drive cycle of the vehicle, and drive cycle is associated with different thing in the vehicle, and in the end, your battery SOC is dependent on that. Okay, like desired speed, desired acceleration, desired force, desired torque, actual speed, actual acceleration, actual force, limited torque, and then motor power, battery power. These are the variables on which the battery SOC is dependent on. So sometimes you have been seeing that you have seen that your battery BMS system track keeps the record of your vehicle operation. It logs the data, the way the vehicle has been driven in the past. So it will have history of each day, and based on the history, your BMS algorithm predict the best performance of the battery. So it is depending on drive cycle profile of vehicle. Okay, and there are many dependent parameter under which this SOC is calculated. So yeah. Now comes to cell balancing. So cell balancing is one of the main aspect of battery management system. So cell balancing is very very important, and it plays a critical role in battery management system or battery pack. So cells, we know that each cell are having some limited voltage, limited current, and limited SOC. Okay, so there are different chemistry battery cells. So most commonly is like lithium ion battery cell. The voltage range is between the operational voltage range is 3.5 volt to 4.2 volt, and the ampere hour rating, let's say 5 ampere hour or 6 ampere hour. So this is the battery cell, and from this battery cell you are going to make your module or battery pack. So if you have to increase the DC bus voltage, your cell is going to be connected in the series fashion. If you have to increase the capacity or power rating of battery pack, then your number of cells is going to be connected in the parallel fashion. So with this topology, you will have some series and parallel combination of battery cells. Tiny cells are connected in some topology fashion, and it makes out the battery pack. So the battery pack is pre-calculated. What is going to be your DC bus voltage? What is going to be the ampere hour rating of your battery pack, and it is all depending on the type of vehicle which you are going to use. Okay, whether it is two-wheeler, three-wheeler, and the load of that vehicle, and the passengers, and the terrain it is going to driven from or driven on. Depending on that, then the battery rating or capacity is going to be calculated, and then which chemistry cell battery is going to be used, and how many modules are going to be there, and which type of battery management system can be used for this battery pack. So yeah, so it is a complex architecture, and then cell balancing plays a very important role when it comes to get the good performance of the battery pack or vehicle, when it comes to the aging of the battery pack, when it comes to the density of the battery cells, are getting the good range or good performance out of that, and the safety, and the charging and discharging of the battery cell. So we know that these cells are may not be unique in their manufacturing when it comes to combine number of cells all together. So there might be some defects in each cell, but with respect to that given condition, you have to get the best performance out of them. Okay, so some cells might be weak, some cells might be strong, but cells are connected each other. So if any one cell is giving you problem, so you need to address that problem. So battery management system has to ensure that. So battery management system will monitor each battery cell. Okay, it will monitor each battery cell, and it will find out where is the fault, and how to address that issue. So this is a complex architecture. This is your BMS, this is someone else BMS. Okay, so whichever BMS it is, it has to take care of that. So now, better the BMS, more the cost, more the complex architecture. Simple the BMS, less performance, less safety precautions, cheaper the vehicle, like that. Okay, so when battery is charging and discharging, it is impacting the battery cell behavior, electrochemical reaction. Okay, so when there is a weak cell connected with the strong cell in series or parallel combination, so a weaker is always impacting because they are in series connections. Okay, so the weaker cell will charge very fast and discharge very fast. So it will have its own capacity, the rating of the battery cell, and the other cell may have the different capacity of battery cell rating. Okay, and the time response of each battery cell also matters, how fast it is charging, how fast it is discharging. So it has to it is clapped together. One cell has to follow other cell, whether it is slow or fast. However, the cell is capable, it is strong, but it is getting impacted by other cell, which is like weak cell, which is getting very fast and very charge and very fast discharge. So how cell manage that? So it is not the job of cell, it is the job of battery management system. So battery management system identify a particular cell, and it tries to equalize the performance with other neighboring cell. It try to find out the states of battery cell, and provides the best path or best operating condition for battery cells. So here is the case when we have battery unbalancing, cell unbalancing, and battery cell balancing. So in unbalancing case, we see here the cells are having different charges in each cell, and with the balancing, all the SOC level of each battery cells are same, looking same. So this balance condition is going to give you best performance. You are able to extract very good energy from this battery cell compared to the unbalanced cell. Unbalancing can be a reason from different way. Means we are going to see that what are the reasons why the battery cells are imbalanced. So there are different aspect for that. So this is just to understand which is the balance or which is unbalanced. So we can go ahead. Cause of imbalance. So yeah, so there are two main important points here for causing the imbalance. One is with the cell is strong and weak. Okay, so if the cell is strong and weak, then there will be imbalance. So that means the weaker cell are faster in charging and discharging, and the strong cell is like a nominal type of operation, the predicted or the certain operation that is the strong cell. So this is the point, this is the catch. Actually, you have to find out when cells are functional. So you have to identify what is the strong cell and what is weak cell. So it is very difficult to find out. So when the cells are clubbed together, so from their starting, some cells are weak and some cells are strong. So that means they have fixed time response. That means they take this much of time for charging and this much time of discharging. It is fixed in the starting when you start using your battery. So it is the time response of battery cell, so in terms you are defining, this is the weak cell and this is a strong cell. And weak cell may have like some ampere hour rating, and when you compare to the strong cell may have a little bit more ampere hour rating. Okay, so in that term you are defining this is weak cell and this is strong cell. Another aspect, the weak cell may get aged quickly. That means the performance will be degraded of battery cells when it runs for a long time. Okay, when you have many number of cycle of charge and discharge, so that impacts on battery cell. So how much is the impact on particular battery cell? This is another point of defining whether the battery cell is weak and strong. So there are 2 points. From beginning, battery cell is weak and strong, and over the age, over the time period, the battery cell has become weak and battery cell become strong. Okay, whether it is consistent or not consistent. So these are 2 points which causes imbalance in the battery pack. Okay, battery pack imbalance. So that means cell are getting different SOC level. So not cause of imbalance. So this is the point where the performance degradation is not much on a battery cell. Okay, from the beginning it has been defined this particular cell was weak and this particular cell was strong, and it is consistent always. The over the time period, the degradation has not been impacted much on them. That means it is not cause of imbalance. That means this is the genuine problem which can be easily addressed by the BMS system. That means one cell is having less ampere hour rating, and other cell is having more ampere hour rating, but it is fixed, it is certain, it is defined, and BMS knows about it. So with respect to that, BMS will be able to handle those type of cell based on its strategy for getting the good performance from the battery. Okay, so this is not a cause of imbalance. The cause of imbalance means the cells are getting degraded over the time period. Cells are becoming weaker. Then that is more impacting on the balance of the SOC in each battery cell. So for balancing, there are different strategy which need to be followed for battery cells, for battery pack. So it has to be followed by battery management system. So two broad category of cell balancing are dissipative type and non-dissipative type. So dissipative type will be simpler in design and will be economical, low cost, simple in design, but you may not have very good performance from battery with this type of cell balancing approach. So again, dissipative type, you may have fixed shunt register possible with Jenner type of design, and then switch shunt register type of design under dissipative. And it is mainly uses passive type of component, so like inductor, capacitors. So with respect to that, it has been also called sometime like passive balancing. And non-dissipative type is it transfer the charge between the neighboring cells. Okay, the charge are getting transferred with some circuitry used by BMS with the neighborhood cells. So this is called as non-dissipative and sometimes called as active type of cell balancing. So again, there is categories under that, like charge settling, energy converter, and there are some other categories also. Okay, depending on the topology you are going to use. The circuit you are going to use, the approach you are going to use for the cell balancing. So some of the equalizer circuit, yeah. I still have 10 minutes, I think. I will go quickly and wind up my session. So yeah, so this is cell balancing circuitry, which is like equalizer circuitry. You can see from left to right, A and B. This is kind of some passive component based, the passive type of design, passive balancing circuit design. And right side you have like component, some switches, IGBT, MOSFET, and some passive components are there, and controller for that operating those connections, switch connection. It actually provides the path. So you have cell connection with the BMS, and where the location where the cell are getting connected at BMS will have some circuit. So that circuit can be a simple circuit or can be a complex circuit, depends on the approach of the cell balancing and the BMS architecture. So whether the BMS has the feature of active cell balancing or passive cell balancing, based on that the circuitry is designed where the cells are getting connected with the BMS. So these circuits provides the path between the cell so that they can transfer the charge, and there will be switches are routing decided by BMS control algorithm. So the control algorithm estimate the state of the battery cells, voltage, current, temperature, SOC, charging or discharging. Based on that, it decide which cell need to be balanced with which cell is weak, which cell is strong. Okay, so this is the equalizer circuit. And there is another important point here to control the contactor. So high voltage contactor, which is with the battery cell terminal. As I said, the battery cells are making the battery pack. So the battery cells are there inside, but out of those connections, you have to have main point of connection, the high voltage terminal of the battery. So that high voltage, because you have the battery pack, that means you have high voltage terminal, positive and negative terminal. So which is a battery pack output, so DC output, how you get it and where you connect and which hardware you are going to connect. So battery have pack capacity, you have two terminals, positive and negative terminals. You are going to connect with the drives, you are going to connect with the traction inverter, you are going to connect with the load. So now battery is having high capacity. Earlier you were talking about the cells, now you are talking about the pack. So high capacity battery, very high voltage, or a very high current, depending on the type of vehicle, whether the battery DC voltage is going to be 48 volt or 60 volt or 100 volt or 700 volt. So the contactor role is become very important for the safety operation or safety precautions. So there are some pre-charge contactor, okay, which are connected with the battery positive terminal and negative terminal. So this ensure the battery is not operating in bad scenario, like during charging and discharging you may have some inrush current, okay, and that may damage your component, hardware component or load side or battery side, okay. So to have a proper tracking of that, the proper follow of curve of charging and discharging of the battery, you need to have this contactor. So these contactor actually are operated by battery management system. So when you charge, you need to follow the sequence A, B, C, D, E. So A, when you see A, there is no connection, and the contactor is not connecting with the battery pack with the DC bus side. Okay, so these are the pre-charge contactor. Negative contactor and positive contactor will be there, and pre-charge contactor will be there. And if you see the B, so in the B, negative contactor is connected and other two contactor are open. In C, positive negative is connected, and the pre-charge, oh sorry, that is E. The C is below, in the left corner below. The C is negative is connected and pre-charge contactor is connected. Positive contactor is still not connected. And D, if you see, positive, negative, and pre-charge contactor is connected. And in E, you have pre-charge contactor open. So this provides you the proper operation of battery pack when load is connected other side at DC bus. So you need to have pre-charge contactor which is maintaining the transient behavior, transient condition. Once it got the steady state, then the pre-charge contactor will open, other two contactor will remain closed. So now coming to the real-time simulation, the role of real-time simulation for validation and testing of BMS system. So as we know that test by experience, it is difficult to handle, logistic and impact, expensive, sometimes hazardous, power systems are involved, moving part are involved. So you go with the real-time simulation approach where you have mathematical modeling of your system. We discussed that battery model need to be modeled, need to be there to have proper testing and validation of BMS system. So some kind of real-time simulator will be required. With that, you can actually validate your physical controller or physical battery management system. So these are some of the common points which tells you, which invoke you to go with the real-time simulation, because there are limitations when you go with the field testing. You're not able to do many number of tests which are really important, which can only be done inside the lab. So these are some of the points which force you to use some type of software based modeling and mathematical modeling of system and validation. And there is another point which tells you, gives you some indication that you should go with this type of approach, because there are different phases when you develop any product and when you make it operational at end point or end user. So there are different stages when you develop a product: design, coding, implementation, integration, test, system test, and delivery. And the cost is associated at each stage. So where the error has come, so that much of the cost will be there at this stage. So at delivery stage, you have given the product to some customer, you have got the project, but the project should have some outcomes. But somehow you delivered the project, but when it came to actual use, the system or project is not actually being used properly. Means it is not working properly. And when that time, if you have to address that, there will be very difficult to address that that type of project or that type of case, because it involves resources, it involves time, and it involves money. So you have to be very precautious at which stage you are able to identify the problem. And at that time, it is very easy to address and fix, and it takes less time, less manpower, less expertise. That's it. So this is the indication which the graph gives you idea of how you follow your design, how you follow your product implementation. uh, so definition and benefits. So benefits of real-time simulation: it saves the time, saves the cost, saves risk. Save time means you are able to detect your problem early in the V cycle. Save cost means you are able to detect early. That means the other time you are saved. Means the expert, the resources, your time is less consumed, and you are saving the cost. Save risk means you are able to able to create different scenario, different cases, different type of battery designs. You are not able to test the BMS system at the drive cycle. You have to drive the vehicle so long to get the good drive cycle. But with the software environment, you continuously run the model and create different drive cycles and predict different scenario and test your BMS under that condition. So, as we know that this is totally a model-based, mathematical model-based approach, and we have real-time simulator, which allows you to connect with the external hardware, and we have different time responses coming out from the systems. The system we are going to implement for our applications that may be slow or fast, but this real-time simulation allows you to have different simulation rate or different time response based system to be modeled and simulated in real time, which will actually capture the real behavior of the systems. So this is the approach of doing the real time simulation, and it has the definition and benefits for that. And there are different techniques by which this real time simulation can be used, like MIL, RCP, or HIL and PHIL. MIL is total model in loop simulation, where you have a total system in the model form, and you are doing some algorithm and some design changes and optimization. So you work on the model side, and RCP is when it comes to test your algorithm with the hardware. Have flash that algorithm and connect with the real-time simulation, and you can test your software and the hardware performance, your controller of your controller, and the time response and the controllability and the functional testing of that. So you follow the RCP. HIL, when it comes to simulate a bigger plant model, the actual plant model, a drive cycle of vehicle is not able to predictable with the real field data. Then you need to have some design curve modeled in the simulation, where you need exhaustive computation, the very big systems, number of vehicle connected with the grid system. Suppose 100 or 1000 vehicle need to be connected with the grid. So in that case, what will be the scenario, what will be the predictability? So that case, HIL system are more useful. And then PHIL, when it comes to test your device at power level, then PHIL comes in picture. And hybrid is the mix of each, where you have a complex system. You are going to simulate full vehicle, and with V2G application, or with different conditions, for like connecting the vehicle charger all together. You need to have some hybrid type of system. So this is the V cycle you follow with your modeling approach, and go to the implementation with the real hardware, real system, and do the testing and validation. So you follow this V cycle, and you have the platform, you have the software environment, you have the controllers and hardwares. You start your project, and you do implement stage by stage, and you get the good outcomes from that. So yes, it has the visualization and recording. We have these are the features of real-time simulation. So you might be knowing about it, and the automation and compatibility. So the automation actually saves your time. When you are good at it, that means you are able to use these features uh, in a defined or certain way, and you save lot of time. So you perform a test number of times manually, or you perform test same test with the automation approach. You have different type of test, but the same test need to be repeated long many times. So you club the different type of test, and the same test you follow with you do the iteration with the test automation features. The compatibility is to have compatibility with the software and the hardware. You have many different type of software, you have got all those features, so you need to club together and use optimally, whether it is the test automation or whether it is a mathematical model development software, whether it is a programming or whether it is a hardware connection which uses some kind of software to be controlled the hardware. So you have the compatibility, more the compatibility, whether better to use with better to use that. It is easy to use and easy to implement into your system with that. So this is the schematic or capture for which the real-time simulation can be used, like battery pack, electric motor, power converter test and validation, energy management system, mechanical transmission, vehicle body. So this is for full electric vehicle simulation, and yeah, so this is the standard aspect design or the standard systems which you can perform with real-time simulation. So our topic mainly was with the BMS. So these are the some of the point which you can actually carry out or implement or test and validate with the real-time simulations. Like with respect to the BMS, you can have like fault condition testing, charge discharge testing, cell balancing, cell overcharge discharge protection testing, temperature, battery chassis isolation, activation relay and measurements, release test production, CAN communication, all those things you can easily carry out. And then you have the architectures, and these are some of the approach you follow with testing. Hello? Hello?
Oh, yes, sir. Yeah, we can
Can
hear
I,
you.
can I continue for 5 more minutes or should I stop?
I think after this you're taking, or it will be somebody else, sir?
Is
You
it from
continue.
Opalati? Is it from Opalati?
No, no, yeah, yeah. I'm asking, like, you're going to continue the session, or you're winding it up, is it?
Yeah, maybe my colleague Sai will be
Sai sir will be
taking
taking
after
it.
this. So I
Okay.
think this will be discussed in that
Yeah, he
also.
will be taking the Opalati portions in depth, I think. Yeah.
Yes, 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 yes.
There were some
So
questions asked by in the participants have put it in the chat, like how can we program for better SOC estimation with
mhm.
respect to charging and discharging of an EV?
Okay, so there are different techniques for that. I was going through with some literatures and I found that a Kalman based filter approach is the best technique for predicting the SOC and SOH. So it is a software algorithm which need to be implemented, and there are different states which need to be estimated to get the SOC calculation.
Some other question is, which battery has better longevity and take less time in charging? And can we use two different batteries for better SOC estimation?
Yeah, it is a difficult questions because it all depends on the applications, for which application you are going to use battery. So the response time response actually matters for which application you are going to use. The dynamics of getting charge and discharge of the vehicle, the performance, all depends on that the application actually. So I'm not sure I will be able to answer it correctly, but lithium ion is most commonly used for electric vehicle application.
Okay, thank you, sir. And if does any other participant have any doubts they
Ma'am,
want to ask? Yeah.
I have a question, that is it required that all the cells should be connected in series for the cell balancing?
No, not required. The series connection is required when you have some space, some battery pack voltage defined. Suppose 5 volt battery cell are there and you required 50 volt. So 10 cells need to be connected in series. But the 50 volt voltage is not only thing. It is a power. So you need to have the current. So, and each cell will have some current, let's say 5 ampere. So in series, the current is going to be same. So 5 ampere from each cell, that means 5 ampere from series. But if you are looking for more current, bigger battery pack, so you need to have the same string connected in parallel as well.
So that means the cell balancing mostly done based on voltage,
Yeah.
not on
No,
SOC.
no. It is algorithm. It is a BMS algorithm. Your BMS actually monitor the voltage, cell current, and temperature. These are the physical quantity being monitored, and then drive cycle, and then you calculate the SOC. So now cell balancing will be done based on the SOC or based on the. Sometime voltage monitoring is not enough. It may be wrong approach also. Okay, so different parameter you have to address. Maybe temperature also, temperature impacts on SOC impacts on the voltage sometimes is same, but SOC is different. Sometimes there is noise, so you may be not correct on one parameter always.
Okay, and last question. If we have to find out any weak cell, so we will find out based on charging, discharging, or some other parameter also
Yeah,
there.
based on the prediction, based when you charge and discharge, how long it took for a cell to charge and discharge, what is the SOC level, what is the voltage level it has reached, what is the temperature of that particular cell. So when you have the calculation or value of that, you will be able to predict whether this cell is weak or this cell is strong.
Okay. Thank you, sir.
Thank you.
So yeah, we are out of the time also. So like I think thank you, Samir sir, for the like very clearly explaining what are the different procedures which is followed and all, like you have explained it in a very good fashion. And I think next Sai sir will also join with us. So I think we can take a 15 minutes break, and at sharp 12 o'clock, I think we can start the next session.
Okay.
Is Sai sir already connected here?
Yeah, he might be connecting.
Yeah.
Yeah. Thank you so much. Thank you,
Okay.
ma'am. Thank
Thanks,
you
sir.
all.
It was very beautifully explained, and many of the doubts were really cleared when you were taking itself. So thanks a lot.
Thank you. Thank you all. Have a
Thank
nice
you.
day. Bye
Yes,
bye.
sir. Thank you, sir. And Sai, sir, are you connected? We'll take a short 15 minutes break, and after that we will start. And participants, you need not leave the meet. Okay, so you just remind here. You can just turn off your mic and camera, and you can leave, go have some tea or anything, and you can come back after 15 minutes. So sharp 12 o'clock we will start. So we are back, and I think all participants are there. So now we have with us Mr. Sai Teja sir. He is an application Opal Technology India, and he's posted in Bangalore. So he will be delivering you a lecture on this battery management system, mainly the interconnection with Opal and how to do the validation and all. So I just hand over the session to Sai Teja sir. Sir, are you there?
Yes, yes, ma'am.
Yeah,
Thanks for the introduction. I'll start my presentation. I will share my screen now.
yeah, yes, sir.
So I hope the presentation is in
Yes, sir. It is in the presentation mode, and we could
presentation
see.
mode.
Yes.
Okay. Thank
And
you.
1 second, sir. Like Gopal, are you there? Please start the recording. Gopal, I think he went for the break. I'll just check it out. 1 second, sir.
Yeah, sure.
Yeah, he has started. Thank you, sir. You can start.
Okay. So welcome all. Today I would like to give a presentation on validating our BMS controller using HAL platform developed by Opolarity. Coming to the agenda, I will quickly go through the introduction about Opolarity, then the real-time simulation concept, followed by the different types of real-time simulation, and then how we can validate our BMS controller, the various third-party hardware we'll be using along with our simulator for validating the BMS controller. Coming to who we are, Popularity is the world leader in the development of a real-time digital simulator. It has both a PC and FPGA technologies, majorly used for rapid control prototyping and hardware-in-the-loop testing of a controller. Either it may be the controller for a power system or in for automotive industry. So Polarity systems are deployed for design, validation, and optimization of complex control algorithms. It was founded in the year 1997, and we have around 400 employees worldwide. So these are some of our customers. Majority of the customer will be from the electrical domain and also from the aerospace and defense. Nowadays, with the rapid growing in the field of electric vehicles, we are having a number of automotive customers who are using our platform for validating their controllers, BMS controllers. So coming to the difference between a prototype designed and a digital twin of the same prototype. So let us say I'm having the FOC control of an induction motor. So once I have done the prototyping, the same controller, if I want to use it for other motor, I need to have the another motor with me in hand, or else then whereas if you go for digital prototyping, the same I can have the motor model in the simulation, the same controller I can directly connect to the simulated motor and validate our testing. So the here when we compare the analog prototyping coming to the digital prototyping, we will be going to save a lot of time when we go for the digital prototyping with just changing the model which we want to connect for validation of the controller. We can have the simulated model. So directly we can generate the set of equations for the same digital twin and verify our results. This is where digital simulations play a vital role, where the end user might not have all the desired equipment for validating his controller, or else he might have a physical plant but he doesn't have the developed controller, physical controller. Still he will be able to validate his control algorithm by using the digital twin simulation platforms. So here we can understand the difference between desktop simulation and the real-time simulation. The real-time simulation, we can say whatever the results we are getting from these simulated platform will be as good as the results one can expect from a physical hardware. So if we go to the desktop simulation, depending on the complexity of the model, it might be slower or faster. If the model is too complex, then the results we can expect the results within an hour or two. Whereas if the code is pretty simple, the results will be get in a few minutes. But the physical output we may expect after 10 minutes. So let us say I want to close a breaker in a power system simulated model, the breaker should get the command to I need to apply a fault at time t equal to 2 minutes, and the breaker should act at time t equal to 2 minutes. Whereas if we go for desktop simulation, we are not sure whether the breaker is going to close at time t equal to 2 minutes. But when we are using a real-time simulation, we can see that result. The breaker will get the activation command only at time t equal to 2 seconds, and it will close. This is where the effectiveness of verifying the controller happens by using these real-time simulation platforms. So this is one major difference before means when we are doing offline simulation and real-time simulation. When we are doing the desktop simulations, the platform, let us say if we are using the MATLAB software, it may use variable step solver. So when we are using variable step solver, depending on the complexity of the code, the processor itself determines the sample time. So if the code is complex, let us say here, the processor will select a smaller time step in order to collect more samples to exactly give the result. And when the waveform is a bit straightforward, like there is no complexity, it will increase the sample time automatically in order to give us the result in a very fast way. So here, for all the time, it is not maintaining the same sample time, which will which may give the result in a faster way, but it does not allow indeterminism, because we don't know after some time whether the system time step is going to increase or decrease. So that is why for real-time simulations, using the fixed step solver is mandatory. So if we are going for fixed step, then also the performance depends upon the computational burden the simulator can take. So if we are going to have a bigger sample time, we may miss the dynamics of the model. But in order to have a system with smaller time steps, the computational power has to be more, because the whole code, the system should be able to execute the whole code with in a, let us say, time t equal to 10 microsecond. So in order to go for time steps of that kind, we need to have a very high-end processor which can handle these kinds of codes. So our simulators will come with the latest Xeon processors from Intel, which will ensure to run our model with smaller time steps. Coming to the model-based design approach, so this is the process which we follow from our offline model to dumping the code on the real-time simulator and taking the results. So in these rapid design iterations, what we have to follow is we just have to have our offline model. Then for verifying whether the controller is able to, the response of the controller is in accordance to the expected result with the plant, we can have our physical plant and simulated controller. Whatever the signals we want to send to the plant, we can send it using the IOs available on the hardware. And the feedback we can take from the physical hardware, we can step down them and give it to the as analog input to the simulator, and we can validate our controller. So let us say if the response is not as expected, we can again rapidly change the controller parameters and automatically generate the C code. So we need not to have to generate the code expected for the real-time simulator. It will automatically taken care by our software. We just have to change our parameter, and on the fly we can verify the control algorithm. This is how the model-based design approach will work. Now coming to the simulator architecture from Opalati, our will be having one central processing unit, one processor, and also one FPGA. So I will explain now. So each simulator will be having a processor and an FPGA. So this is the place where we'll be going to execute our model and take the results. So let us say the equipment under test is a physical hardware. So in order to establish the communication between these two, the FPGA will drive these IO channels. So by using the FPGA for driving the IO channels, we can have the signal latency will be in the order of a very few microseconds, which is really good in sending and receiving the data with EUT. And host PC is the user interface where the user will be having his MATLAB model. The communication between the real-time simulator and the host PC will be via Ethernet card. So every simulator will come with an IP address. Using that, we can connect with a real-time simulator and then dump our model onto the real-time simulator and execute our model. So if you, in future, if you want to go for IO expansion, we can do that by easily connecting one expansion box. So let us say I have only 16 analog IO, but I require 20 or 30 analog IOs. So we can take one IO expansion box with an additional IO card, and we can happily expand our IOs. So every simulator will come with analog IO and digital IO. And also we are having a number of protocols. We'll support a number of protocols. For automotive application, we are supporting the CAN protocol. Whereas for power system studies, we are supporting IEC 61850 C37 protocol. So like that, our simulators will support different various kinds of protocols which are useful for connecting to the DUT. This is the architecture of all the Opalati simulators. This will be similar. Only the so here we can see different real-time process simulators from Opalati. The difference between these lies in the number of the CPU cores, the processing power, and the IO channels. So this is our basic version where we are going to have only one set of analog IO and one set of digital IO with a four-core processor. Whereas if we go for this high-end 5707, it will have more number of processors. So if we are having a very complex problem, we can divide our code and execute it on parallelly on different CPU cores. In that case, we can go for this high-end simulator, or we can go with the basic unit. So these are the various kinds of real-time simulation one can perform. So once we have the offline model, initially we can start with model in loop simulation, where the controller and the plant, everything will be in simulated environment. So in the model in loop testing, we'll first validate whether the result what we are getting from this model in loop simulation correlate will be as decided by the user or not. Once model in loop results we have obtained, we can either go for rapid control prototyping or hardware in loop testing. The only difference is in rapid control prototyping, we'll be having a real plant and we are going to fine tune our control algorithm, because the control algorithm will be inside the simulator. And by using the analog and digital IO channels, we can establish the communication between the physical plant and the simulated controller. In this way, we can fine tune our control algorithm depending on the response from the plant. And then we can go for hardware in loop testing, where our control algorithm is dumped onto a real controller, physical controller, and we would like to see the response with a simulated plant. Before this is used for validating our controller in safer environment. So before connecting to a physical environment, physical plant, we can validate our controller with a system plant model simulated. And this is also a case in hardware in loop testing known as power hardware in loop, where let us say we are modeling a controller for a distributed energy resource. Like we have a model for a microgrid, and we also have the distributed energy resource available with us, like a PV array or a wind emulator. So before commissioning this control algorithm onto the main grid, what we can do is we can have a power amplifier in between and connect our microgrid controller with the our dynamic energy resource and establish the communication between the grid and the physical microgrid by using these power amplifiers. So these will help us in connecting these DERs to our grid with the voltage and current amplitudes, uh, voltage and current signals which are in accordance to these DERs. So let us say here I'm having a 1 kilovolt signal, but my real-time simulator will only take 16 volts. So the power amplifier will take care of stepping down the voltage level and sending it as a feedback to our simulator. We can amplify it to the level of required by the DER and connect it. So in this way, we can validate our controller of an developed for a microgrid before giving it to the operator, we can validate the functionality using this PHIL approach. This is the next level testing of hardware in loop, whereas here all the signals will be in the level of not more than 30 volts, whereas here we can go for connecting a physical DER for the controller. These are the various types of real-time simulation one can perform. Now, coming to today's topic, first I would like to introduce a brief on battery management system. So, to enhance the performance of an electric vehicle or a hybrid electric vehicle for its operational service length, the time period at which it will be going to use, and also for maintaining the safety of the battery, safety of the end user who is using that EV. So the energy storage system in the vehicle is a vital part for all the EV technologies. So if we are not taking care of the good health of a battery pack or a battery cell, it will result in unexpected behavior of the battery, which may result in fire accidents, which we can see here. So coming to the battery management system, there are various parameters what the BMS has to take care in order to maintain the good health of the battery pack. So if we are going to have an unbalanced battery cells, so if the under for every cell, if the nominal operating voltage, if it is not inside this limit operating voltage limit, then because of this undercharged cell, the pack we may see the voltage is somewhat as expected, but this cell in a very near future it will be going to we may not be able to charge this cell again. So in this kind of behavior is not expected when we are going for battery packs. So the BMS should take care of individual cell voltage, current, temperature. It should monitor every time, and it should make sure that all the cells will be having at least will be operating within the safe operating area. So this is what here we can see. We can define a battery management system as a system comprising of various devices responsible for managing.
So, a small doubt here, like say you have a set of cells, say 10 or 15 cells. So like
Okay.
for each and individual cells, the data will be taken like how, like usually if we see the whole cell, we will be seeing the voltage and current, or like the
Yes.
whole battery, or
Whole
is it for individual cells also, we will be collecting the data to see like which of this cell has gone
Yeah.
overcharged or something?
Actually, each individual cell data we need to take care. Then only we can ensure the health of each and individual battery cell. So if I say battery, it may have a number of cells, but each individual cell data is we need to take into account when we are going for the BMS algorithm for any EV. They will be taking they will be monitoring each and every individual cell data. Then only the pack voltage we can maintain.
Okay, okay, sir. Fine.
Yes, yes. So the battery management system, it comprises of various devices responsible for managing a rechargeable battery cell level, cell module level, and the pack level. So here we can see it should take care of at the from the cell level and the health of individual module, and at the pack means all the modules are connected either in series fashion or else in the parallel fashion. So in all these levels, it should take care of all the data. Then only we'll be able to what should I say? We'll be able to manipulate each and every cell in order to make the battery pack in a healthy state. So the BMS comes with two control layers. One is the supervisory layer, and the other is the battery monitoring unit layer. So the battery monitoring unit is the place where we'll be taking the each individual cell data, the voltage across the cell, the current and the temperature, and it helps in maintaining the cell, in performing the cell balancing, either active or passive balancing. So this acts as a slave to this supervisory BMS. So the supervisory BMS will take all these voltage, current, and temperature data from the battery monitoring unit, and it is the top level controller. It will help in taking the decision. It is like a decision maker. So depending on the health of individual cell and also the pack voltage and the pack current, how much load it is connected. So depending on all these, it will take the decision either to charge or discharge the battery, and also either to if the if one of the cell is not is going to discharge in a faster rate, then it will help in decreasing the decreasing taking the current from that battery, and it will help to charge that individual battery. So everything will be happen by using this supervisory BMS. So these slaves will all be communicated to one supervisory BMS. Here we can see we will be having n number of slaves which are connected to individual modules. All this data the supervisory BMS will take care and try to take the either to charge or discharge, but that particular module, it will take the decision and perform those balancing commands. This is what the battery management system is all about. So we need to take care of individual cell, then only we can maintain the health of the battery. Now, so the main functions might be all these we can take out. So the supervisory will be taking the data from the BMU, the battery cell monitoring, all for each and every voltage and current across each and every cell we can do. So this is what we can do by the solution proposed by Opality for testing your BMS. So you can have we can perform the cell balancing, equalization. All these are the main functions which we can do by using the solution which I am going to propose now. So as I explained in the previous slide, for the BMS also, we can have either software in loop kind of testing, and then the rapid control prototyping and the hardware in the loop. So when we do software in the loop testing, we don't have any physical hardware connected. So this is for the initial study. Now coming to the rapid control prototyping, here the real plant will be a battery pack. So if we are going for a rapid control prototyping kind of testing, we will not be able to cover all the test cases which we want to do with the controller, because for a real battery we can't apply a short circuit, and that kind of a fault we can't apply. Whereas coming to the hardware in loop kind of testing, where we are having our controller, and we want to verify whether the controller is able to read all the data from the battery and do the corrective action or not. So this is the most popular case for BMS testing, where the user will be having his real controller, and we are going to simulate the battery pack inside our simulator. All the data of the battery will be sent to the controller via, most of the time we'll be using CAN communication, or automotives will be using isolated SPI communication for reading all this data. So using the CAN channels, normally we will send the voltage, current, temperature, all the parameters of the battery from the simulated plant to the controller. The controller will read all the data, and it should be able to give the response in such a way that if the unbalanced cells are there, it should perform the balancing. And if any cell, the rate of discharge is very high, then it should reduce the load across that module, and it should try to balance that cell. So all these kind of things we can verify, and also on each individual cell we can give a number of fault scenarios like the open circuit, short circuit, polarity reversal. All these kinds of faults we can apply on these simulated batteries, and we can test our controller whether it's able to do the corrective action or not. So this is how we are proposing, Popularity is proposing the solution for BMS testing. So either the workstation might be with MATLAB or Veristan. Both we can have. If we are using Veristan software, then we can take the PXI chassis as the hardware and do our testing. Or else if we want to have a model with a MATLAB centered model, and then we can have the Popularity simulator. So we are going to simulate this battery plant in our host PC and dump it on the real-time hardware. For emulating the battery, we have a third-party vendor named as Comemso. So Comemso will provide us battery cell simulators, which will try to emulate the exact behavior, whatever the battery behavior we have defined in our plant. the same battery commands we can send to the COMIMSO, which will emulate that hardware behavior, and the voltage and current and the temperature across this battery cell simulator, we can send it to the controller, our device under test. So this is how the hill setup will look like. I will explain about each individual unit in detail here. So this is how the hardware will look like. This is the DUT from the user, and the batteries we are emulating on this hardware. I will go to the next slide. So in this hill testing also, we are having different ways of testing. It will be like individual cell testing or the whole pack testing, depending on the requirement from the user. We will propose the solution. So if it is a traditional cell emulation where we want to understand from the cell level, individual cell data we want to take, and individual cell we would like to control. So then we'll propose this COMIMSO BCS emulator. And if it is a hybrid where we want to have individual cell data as well as the pack level voltage and current, whether it is able to maintain, and those commands we would like to send to the BMS. Then for maintaining that pack voltage and current, it will be able to do with these programmable power supplies. And if we go for full pack emulation, which will be having around 500 cells or 1000 cells, then that kind of voltages and currents will be maintained by these emulators. On these data we can send to our BMS, and we can test our BMS. So if our BMS is like, if we want to test in the cell level, we can take the hardware from the COMIMSO, and the battery data, whatever the voltage and current we want to set, we can send it from our SPS battery model. So here we can define the behavior of a battery. So it may be lithium ion or nickel cadmium or lead acid center. So the type of the battery we are going to define here, and how it should means the nominal voltage and the capacity and the characteristics. Once we have defined here, these commands we are giving to that battery cell emulator, which will helps in emulating the exact electrical behavior of this battery. And from there we can send the data to the our BMS, because BMS will take the ratings of 5 ampere, but from the real-time simulator, let us say each cell is rated for 4 ampere or 5 ampere. That 4 ampere or 5 ampere command we will not be able to get it from our real-time simulator platform. So in that way, we can send this command to the battery cell emulator, which will act as a source or a sink of 5 ampere. That command we can send to our BMS, and we can verify our algorithm. That is where we are using the third-party hardware. So this is the whole setup of the traditional cell emulation components. So for our BMS, we can have the high precision battery cell emulation from one hardware, and then for setting, because the battery characteristics will be changed with respect to temperature, in order to verify the effect of temperature on our battery, and once this is changing, the voltage should change, and that commands we need to send it to our BMS. So for that we have an NTC or PTC sensor emulation, which will help us in sending these temperature commands of the battery. So this helps in maintaining the electrical characteristics of the battery, and this sensor will be helping sending the temperature of individual cell. And then for any battery pack, this isolation distance is also an important parameter. So between the positive and negative terminals of the battery, every time there should be, ideally it should be like a infinite resistance should be there, but very huge resistance should be there between these two, so that there will not be any closed path between the positive and negative of the battery. So if any, due to some failure, if the insulation resistance breakage is happen, then how the BMS will act. In order to test that kind of a scenario, we are having this insulation check, insulation resistance check simulator. So it will help in varying the resistance between the pack voltage, and we can send the same command to the BMS. So all these hardwares are required for testing our BMS in a safer environment. If we take a physical battery and connect it to the BMS, we won't be able to test all these conditions. But with this setup, we'll be able to do all this testing. So here we can see that. So these are from the comments. So each individual BCS can maintain up to 8 volt, and we can emulate 12 cells from one unit. And also the current can be go up to 6 ampere per cell. And if because of any issues, if any damages happen, then individual cells can be replaced. So it will helps in emulating the our battery cell. So we can have a virtual battery cell in our model, and then send the same data to this BCS unit, which will emulate that behavior and send the commands to our BMS. So let us say we'd like to test a battery pack with around 500 or 600 cells. In typical case, what happens is, as I said in the previous slide, there will be a master BMS and a slave BMS. So the slave will take the voltage, current, and temperature data from individual cell and send it to the master. The communication protocol here, this ISSPI is isolated serial peripheral interconnect. So in most of the automotives, they'll be using this ISSPI communication for establishing the communication between the master and slave BMS devices. So let us say if I'm going to have around 500 cells, then we can't have those many cells emulated by using this hardware. That is where okay, I will explain about that solution in the coming slides. But this is how the traditional setup will look like. We will be having our battery model in our hardware. The same data will be sending to this BCS. The communication protocol used here is a CAN protocol, because most of the automotives will use CAN for establishing the communication between different ECUs available inside the vehicle. So the same CAN protocol, these BCS units will also respond only to the CAN protocol. So whatever the data we are having for each cell, we can send it to these units via CAN, and the slave devices will monitor and tries to perform the active balancing depending on the communication with the master BMS. Coming to the NTC-PTC simulation, here we are having cards which will emulate the resistance. So by changing the temperature value, it will change the resistance. We can go up to 8 mega ohm. So we'll be having one lookup table in the model where we are going to define it's a predefined table. One lookup table will be there where the resistance will be corresponds to for a point of temperature. So let us say if I apply 32,000 ohms, then it will correspond to 25 degrees. Like that, we can change this resistance and the corresponding temperature will vary. That command we can send to the our BMS. So this is how we can connect to our BMS. So all this NTC-PTC emulator will also work with the CAN protocol. From the simulator, we can send the data, and the same temperature data will be sent to the BMS. As I explained in the previous slide, for isolation check also, we are having the range from 20 kilo ohm to 65 mega ohm. So if the pack is under healthy condition, the resistance will be around 65 mega ohm, and we can with a pack voltage of 1 kilo ohm, we can 1 kilovolt, we can test that isolation breakage testing. So due to if any abnormal condition, if what if there is a short circuit between the positive and negative of the battery, so then we can reduce the isolation this resistance value, which in turn will be detected by the ECU and should give this kind of a command: the resistance is low, isolation resistance is low, we should not use this pack. For that kind of communication, we'll be using this isolation monitoring setup. And on each individual cell level, we can apply all these test cases. these are some of the test cases. We can also extend to FAU, failure insertion unit, so you can have more number of tests when compared to these. These are like for individual cell, we can have these kinds of these three tests: broken wire test, short circuit test, and polarity reversal test. Okay. So as I explained in the previously, emulating the whole battery stack cell by cell can overkill the time, because if we take the Tesla Model S, it will be having a module of 444 batteries. N number of modules will be there. So if we want to emulate this kind of battery pack with the Comenso hardware, it will be tiresome. We won't be able to test it. So for this, what we can do is, in order to read a detailed cell emulation for small number cells, we will go for this battery cell emulator. And for taking the full stack voltage and current, we can do that by using the programmable power supplies. We can have both the setup in the same bench. The pack cell voltage and current, we can send it from the power supplies, whereas individual cell data we can take from this Comenso hardware. And both can be connected to the our BMS. And also Opalete has come up with another solution called as cell monitoring device emulation. I will explain in the next slide. So as I said, the master BMS and the slave BMS, they will be communicated via ISO-SPI, and these are some of the transceiver slave chips. So these will help in reading the individual cell voltage, current, and the temperature. Most of the time, they'll be using these chips either from analog devices or NXP, or we have some other companies which will give these boards which can sense the battery voltage current via the CAN messages, and it will be sending to the master BMS via ASSP. So if we have more number of batteries, then in order to have the physical BMS slave is also tiresome. So in this case, what we can do is, what this cell CMDE will do is, it will emulate this slave chip behavior on the FPGA of the simulator, and we can send the battery voltage current data from the model itself to these slave chips directly. We might not need to have a battery cell emulator or a physical BMS slave. Both we can simulate, and the data we can give it to the master BMS. In this way, it helps in testing increasing our testing capability, because it is not feasible to have a more number of emulated cells or a more number of battery slaves. So we can simulate both the battery cells and also the BMS slave on the simulator itself, and the same data can be sent to the master BMS via ISO-SPI. So this protocol also we can emulate and send the data to the master BMS. This is what the cell monitoring device emulation is all about. So battery cell will be modeled in Simulink, and also it may be a compiled code. It can be brought to the RTLab environment if we are using Opalete simulator, or else the NI Veristant if we are using the NI based hardware. So in the real-time simulator, the same battery model will execute, and whatever the values of the different parameters of the battery we want to send, we can send to this emulated transceiver to the DUT. So this is the architecture. If we want the feedback, we can take the feedback from the master BMS also, either in the link or in the ring way we can have this CMDE. So here we can see the example. We'll be having some emulated cells and also some simulated battery cells. Both the cell data. So this is LTC 6813 chipset from analog devices. So the physical voltage and current data, voltage, current, and temperature data of the battery, we can give it to a physical chip and send it to the master BMS. And at the same time, same board can be emulated on the FPGA, the voltage and current of the simulated cell. So for testing more number of cells, So here, let us say I have only 24 cells which are physical, and the rest 500 or 600 cells, I can simulate it on the FPGA. On the CPU, I can have the battery simulated and send the same data on the FPGA to the master BMS. The same protocol, whatever this chipset will use, the same protocol we can emulate and connect it to the master BMS. This is how we can use the CMDE solution from the Opolarity. And for the full pack testing, we are having one third-party vendor known as DNV Electronics. So battery pack emulation has a wide range of application, like for interacting with various charges for the application like vehicle to grid to vehicle, DC-AC, fast charging and all. So for this, we need to have the pack level data, pack level testing. Before we give it to a physical, connecting to a physical charger, our controller, so we can have a DC emulator from DNV. So interaction with the physical inverter we can have, or a DC-DC converter and other HDC loads, we can have a DC emulator and verify our algorithm. So these are some of our BMS test bench users. We have Caterpillar, Tata, Array, Rivian. So they are using for testing their BMS controller for cell balancing, isolation monitoring, and temperature verification. Then they can have multi ECU. As I said, in an electric vehicle, BMS is one controller, and along with that, we will be having a number of ECUs for different applications. So they can establish the communication between the different ECUs. By using this solution, they can have the different ECUs also and connect it to the test bench and verify the results. Like they're having a ECU for motor control and also another ECU for pump control. All those ECUs can be interconnected to this battery pack. So the next stage from this battery will be a inverter. So ECU for the inverter also they can connect, and whatever the commands it is going to have from this BMS intercommunication we can establish. So thanks for your time. I'm happy to answer any of the questions.
Yeah, thank you, sir. Like, and I also would like to add up, like in Sweden, there is a company Northvolt which is fully manufacturing these batteries only. They were also like once when I was discussing with them, they were getting Opal RT for testing
Okay.
their batteries itself. It's a full
Yes.
only battery manufacturing company and mainly lithium ion based batteries and of very big size. They were showing the photos and it was like more than 2 3 people standing together. So such high batteries were there. That's
Yeah.
mainly for I think solar based plants and all. They were manufacturing very big and even for electric vehicles.
Yeah.
So
Yeah.
they
Like
were also telling they were using emulators and they were asking about Opal Artisans. At that time, I had worked with all these. They were asking about Opal RT for the testing because they had started emulators for testing their
yes.
battery systems. So many
Okay.
industries, like as you had also shown, Tata and many other people are also using it. Yeah, I think participants, if you have any doubts or you want to clear, you can just ask.
Hello, ma'am. Hello, sir. I
Yeah.
have a one question.
Yeah.
Can we use the battery emulator as a fuel cell or supercapacitor? Or that only use as a battery emulator as a
Means for fuel cell ultracapacitor, the behavior will be different when compared to lithium ion battery or what should I say, nickel cadmium. So if we are able to send that fuel cell data to the emulator, it will be like emulating that behavior also. So it will emulate only the electrical behavior of a individual battery. So I will show here. So
Is
these
it the, sir, is it the mathematical modeling what you do and put it here? So might be we have to do the model of the fuel cell and put it
Yes,
here.
yes. Yeah, yeah. Then we can send those data via the CAN communication to this unit. So this unit, what it will do is it will emulate whatever the data we are sending. Let us say if it is for a fuel cell, the same whatever the voltage and current, the rating will be 8 volt and 5 ampere for each cell. So it is in the user hand what kind of characteristic he want to send to this unit.
So we can't send this data through the MATLAB if I have a mathematical model.
Yeah. Means via the same data we need to send via the canvas. We can it will emulate the same behavior.
So I think what is asking is in MATLAB also we can do the same. Then why is this required? Is
No,
it?
no. Means if we
No,
have
I'm
a
asking this question like the
yes.
person.
Because I need like a hardware or not. If I'm using battery emulator, I need actual hardware or not.
Battery emulator is itself the hardware, and you need to have the physical BMS. The DUT will be your BMS algorithm.
He's
No need.
asking whether you require a fuel cell or you
No,
can
no,
just model the
no.
fuel cell.
We can model the fuel cell. The
It is
physical
not
hardware is not
required that
required.
you should have the fuel cell as
No,
such.
no, 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 no.
But one thing is, if you're not modeling, I think from data you can collect the data from the fuel cell, and that characteristics can be put here. So this will act as an emulator there, which will act like
Yes,
a real fuel cell.
yes,
Same
yes.
thing happen for the supercapacitor also.
Yeah.
We can model our own supercapacitor, own battery, and can we emulate on this battery emulator.
Yes.
And if I have to replace this emulator with the physical battery, what additional component we required?
Physical battery means it will be the final testing, right?
For example, I have first test with the emulator. Now I
Okay.
have to replace the emulator with my physical
You
battery.
connect the
What?
physical battery there. That's it.
Yeah, that's it.
The BMS is there. No? BMS is the control logic. Okay, so you have done the control logic. Now, say for example, you don't have a solar panel. You want to test that solar panel. You make a model and put it here. You test your controller with it, and it will give you an characteristic similar to that of the real solar panel. So here also it's the same thing said. Say suddenly you're creating a short circuit and you want to check or the imbalance of this different cells. You are checking it. So sometimes like in testing in a real system will be very difficult. Okay, like because you're giving a short circuit, how many times will you give short circuit? It may get damaged and again you have to do. So this is an emulation. It will not. It will show you the extreme values. With that, you can understand. Yeah, your thing will be in problem. But what you're asking, I could understand that can be done in MATLAB itself. Why do you want to go for this? In MATLAB, sir was telling like their variable step is used and there the characteristics it is not with respect to real time. So many a times when you do a simulation, the in hardware it will be different. When you go and implement it, the controller will be operating in a different way. So now you are trying to emulate that same system here, which will give you a more accurate result than the simulation. That's the only thing what we are doing here. Even big companies, before testing that model in real time, they do the emulation than the simulation. So this is a better environment than simulation.
Sir has shown one diagram where they are using a battery emulator also and the physical battery also. And when he connecting the
Uh,
physical battery with the system, he's using FPGA. So then my question, we need an additional FPGA for that or
no,
not?
no. Yeah. I will show that. Yeah, this is what you're
One.
speaking about, right?
Sir.
Yeah, so here this is like the because when you want to test your algorithm, let us say your battery pack has around 700 cells. Okay, we can't emulate all the 700 individual cell by using this emulator. It will be very costly. So what we have proposed is we can simulate the cell and the data to the master BMS. We can send via these LTC chips, which will be going to have the exact behavior as a physical slave BMS. Okay. So the data, whatever transferred from this physical slave BMS and the emulated slave BMS will be similar. The same data we can send to the master BMS. So for master BMS, it is like 700 cells are connected, but the user will know only 36 are the physical cell, means physical emulated cell, and the remaining are the simulated battery cells.
Okay, sir.
Yeah. So in order to test all the 700 cells, we can't emulate all the 700 cells on this, but the as the model is running on the real time, whatever the data sent from this physical slave BMS and this emulated slave BMS will be the same.
Okay, and one more question. If I have only one cell, physical cell,
Yeah.
Because when we talk about the simulator, real-time simulator, they have a digital input output, analog input and output. So how we
Yes.
can decide that how many input output we required if we're using only one cell on the basis of that?
Means it depends on your algorithm. If you your algorithm means you won't be rating the algorithm for a one cell or two cell. It will be a pack. So depending on that, and all these data communication is happening via the CAN bus and the ISO SPI. So analog and digital will not be using, the IOs will not be using, the communication protocols we are using for sending this data to the DUT. So it depends on your DUT whether it takes the data from the analog or digital, or via the CAN it will take the input data. Depending on that, we can comment on the required analog and digital channels. So the
Okay,
begin,
thank you,
yeah.
sir.
Yeah, any other participants, if you have any doubts?
Yeah, actually, my one question is that, sir, is it at the academic or institute level, is it really possible, let's say, to frame or to let's say design and develop our own battery management system? Actually, basically, what we are doing, we are just purchasing directly from the market, okay, ready-made BMS, and then we just try to explore it and just try to let's say develop our some algorithm or let's say some input or the output connecting devices. So,
Yes, yes.
sir, how it is difficult to develop our BMS, because actually we are working on some hybrid vehicles or let's say electric vehicles. So each and every time, let's say we need to go to purchase the battery on a ready-made mode. So the BMS is already itself inbuilt in the battery
Yes,
itself.
yes, yes.
So how it is difficult, sir, to develop this BMS at all at this academic level or institution level?
Institution level, like because the BMS, the algorithm is one part, and then for establishing the communication with an emulator or else the physical battery, let us consider. So the data transfer we need to like establish via the various communication protocols. So defining those protocols and then developing that hardware, it will not be feasible with the academic. So most of the academicians, what as you said, so you can have a physical means readily available BMS, but on that you can develop your own controller and dump on that uh, readily available BMS controller. You can dump your code and then you can test your BMS, because all these communication protocol and all we won't be able to do it. So the physical, whatever the readily available BMS, it will come with all those required protocols and IO channels and all. So to that we can connect the battery emulator and we can test your control algorithm.
Okay, sir. Okay, fine.
Yeah.
Any other participants? So, Sai Teja sir, thanks for the wonderful lecture, and we request you to please share the slides also with the participants. It will be very useful for them.
Yeah, sure, ma'am. I will share you the presentation.
Yeah, yes, sir. And please tell Samir sir also, like if he can also share
Yeah,
the material, that will be very useful for our participants. And on the last day, they have a MCQ also. So for that also, it will
okay.
be helpful.
Sure,
Yeah.
sure, ma'am. Yeah, I'll do
And,
that.
thank you, sir. Thank you for joining with us. And it was really a very good experience learning about how this system works or what is the battery management system. So you had given all your insight about that. And first of all, thank the whole Opal RT team, because and even you, because with the short notice yesterday, because I wanted somebody to come and explain the battery management basics also, and you did that, and I really thank you for getting Samir sir here also. And thank you, sir. Thank you once again for joining with us.
Yeah, thank you, ma'am. It's pleasure giving this lecture.
Okay, thank you, sir. And participants, today afternoon we have with us Ravi Teja sir, who will be giving you an insight on the motor, like the drive, electric drive system. Okay, so that's also a very wonderful lecture. Sir has a very different method of teaching. So I request everyone to join at sharp 2:30 for the next lecture.